uh, 90 to about more than 90 submissions, and the submissions went through a very rigorous review process and of about 20 reviewers. By the way, my name is Subhash and I work for Micron, and I'm one of the chairs here. So there are 10 papers which were chosen from the pool of the almost 90 plus papers which came in from many industries and also some from academia. And so we have Santosh and Alex here. So they are going to be the judges who will be judging for the Best Paper Award. Santosh is from ADI. So it's more than 25 years of experience in digital and mixed signal design. So it's a lot of experience in various companies like IBM, TI, Infineon, Rambus. And so currently is engineering leader at Analog Devices. Thank you, Santosh, for volunteering to be the judge. And he was also the co-chair last year for the user design track. Just let me pull up my notes here. So Alex James, welcome. So he is a professor of hardware, of AI hardware at School of Electronic Systems and Automation, and also the academic dean of Digital University in Digital University of Kerala. So he received his PhD from Queensland Micro and Nanotechnology Center in Australia. So his work kind of covers a broad area, brain-inspired systems, memoristic systems, analog circuits and imaging systems. And also he also heads a maker village that supports over 80 plus hardware startups. Thank you, Alex, for volunteering to be judge. And without further delay, let's go to the first paper today. This is on, I will let the authors to explain more, but this is a novel adiabatic puff for portable devices. This authors are Vishnu, Nalesh, and Kala. So I hope I'm getting the pronunciation right. Okay. So all yours guys, whoever is presenting the puff paper, please come forward. Just a little bit of time check here. So you have roughly about 12 minutes to present, and after then we'll have a few minutes of questions. So it's about let's say 2:20. So you have until 2:32 to present, and then we'll devote some time for the question. Okay, thank you.
A very good afternoon to everyone. Hope you had a good lunch. I'm Vishnu Bajuri, final year BTech student from Jyotishmati Institute of Technology and Science. Here to explain our work title, Novel Adiabatic Puff for Portable Devices. My co-authors for this paper are Nalesh and Kalais. So these are the agenda for today's. So we'll start all the way with the introduction, and then motivation for the proposed work, and then the background. After going through the couple of things, we'll conclude it with the references. So before diving into it, just a quick recap about the portable devices. What are the portable devices? The thing which you are currently holding in your hand is a portable device. It is a device which requires the less power consumption and more security. So some of the examples of the portable devices are, I've listed here, laptops, the mobile phones, everything, cameras, you name it, okay. Coming to the physical acknowledgeable function, two of the problems which has been encountered in portable devices is the circuits which run on the portable devices should consume less power, and also security is very important. To cater all of this, we have used physical acknowledgeable function with adiabatic logic. Physical acknowledgeable function, what is it? So when manufacturing the integrated circuits, no two chips are exactly identical even though they have been fabricated on the same wafer. Ideally, we don't want these process variations. So in the case of puff, we exploit this process variation. Puff exploits this variation to safeguard many of the devices. The input to the puff is called as a challenge. When challenge has been applied, it generates a random output called as a response. One of the application of the puff is it can be used for the device authentication. With this knowledge of a physical acknowledgeable function, now let's talk about adiabatic logic. What is an adiabatic logic? Adiabatic logic is a technique to reduce the power consumption. When compared to the conventional circuit which deploys a DC power supply Adiabatic logic uses what is called as a trapezoidal power clock. So using adiabatic logic, the energy consumption can be reduced, or it is given as RC upon T into C VDD square. Imagine where T is the rise time. If the T is less than twice the RC, the energy consumption will be less than 0.5%. Motivation for our work. What we have done. So while going through the existing work on adiabatic puffs, we have found one disadvantage with these works. When these puff circuits are disabled, they are retaining the response bits. We ideally don't want that. So it was acting like a memory. The attacker might steal the data. So what we have done, we designed a puff such that when you disable it, the response bits are discharged to the ground. So there is no retaining of the data. So below is the example I have shown to indicate. So this is the existing puff, and when the challenge bit has been disabled, it is retaining the previous state. Background and related works. During my study, I have found that puffs can be implemented in various steps. Some of them are the delay-based puffs and the memory-based puffs, which are quite popular. So delay-based puffs are nothing but which exploits the process variation due to delay, and they generate the response bits. If I want to give the popular examples of the delay-based puffs, they are the arbiter puff and the ring oscillator puff. But, these have some disadvantages. They're slower, and they consume more power, which is not suitable for the portable devices. Next category of the puffs are memory-based puffs. Memory-based puffs are very popular. Why? Because they don't require any additional circuitry. Popular examples of the memory-based puffs are the SRAM puffs and DRAM puffs. Most of you mobile phone consisting both of them. So SRAM puffs can work based upon the voltage variation in the transistor. Each SRAM cell can consist of 6 transistors, and if we vary the threshold voltage of each particular cell, this can lead to one cell to be 1, another cell to be logic 0, and can be used as a puff. The same thing applicable for the DRAM puffs. So when powering up the DRAM puffs, due to capacitor leakage values, some of the cells have higher leakage and some of the cells have the lower leakage. So this has been exploited in the DRAM puff. But the above mentioned category puffs suffer from two disadvantages. They consume more power and the complexity is pretty high. To overcome this, there is a category of puffs called adiabatic puffs. So what are these adiabatic puffs? Adiabatic puffs are used for the low power consumption. There were the existing papers on adiabatic puff. They have been designed using cross-coupled inverters with additional circuitry. These puffs also have some disadvantages as said earlier. They retain the response bits when they're disabled. One of the puffs that contain more number of transistors is quasi-adiabatic puff, which has been proposed at ISCS 2020. So there is an idea with the use of a CMOS inverters, we can disable the response bits to ground when the puff is disabled. Okay. Coming to the proposed work. The proposed work consists of 6 transistors actually. 2 pairs of CMOS inverters along with 2 cross-coupled NMOS transistors. So what the thing is, the CMOS inverters has been used to charge and discharge the proposed puff, and at the same time cross-coupled transistors are used to generate the response bits. With this, let us just explain the operation. The trapezoidal power clock supplied to the proposed puff consists of 4 phases. Why the trapezoidal power clock? Because we are using adiabatic logic. Okay. The proposed puff is applied with the trapezoidal power clock, which consists of 4 phases, namely wait, evaluate, hold, and recover. In the wait phase, the VPC will be, that is the power clock will be at ground and the circuit will be inactive, or we can say it's doing nothing, just staying still. In the evaluate phase, the thing starts. So in the evaluate phase, we can see the slower ramp from wait to the hold. So in this phase, we apply the challenge, that is input to the puff as 0. This forces M1 and M3 transistors to turn on. So as the M1 and M3 transistors are turned on, there exists a path from VPC to drain nodes of M5 and M6. But due to gate oxide thickness variations, which induces different threshold voltage in M5 and M6, one node will be charged to 1 and this forces other node to be at logic 0. This is the evaluate phase. In the hold phase, the VPC will be staying at the VDD and the response bits will be stable. Next thing is the recover phase. During the recover phase, the VPC will start to decline from VDD to ground. And in this phase, the output stored or the response bits at the output capacitors will be discharged back to the VPC. We are not dissipating, we are just recovering back to the VPC. That's the beauty of adiabatic circuits via M1 and M3 transistors. So I said earlier, for the proposed puff to be operated, it should be excited with challenge input as 0. So now the thing is, when we excited with challenge input as 1, the response bits which were held earlier will be disabled. How is that? We are using the CMOS inverter. The outputs of the CMOS inverter has been connected to the cross-coupled pair. We know the beauty of CMOS inverter. The output is never floated. It's either connected to the VDD or the ground. So that simple property has been used in our proposed puff cell. 4-bit puff circuitry. We have earlier seen the individual puff cell. So we have cascaded the individual puff cell to make it as a 4-bit puff. So in this 4-bit puff circuitry, we have excited each puff cell with single challenge input. But the VPC supplied to the each puff cell differs by 90 degrees. Why 90 degrees? Because if one puff cell is operating in the wait phase, the next will be operating in the evaluate phase. When they're operating in the different phases, the response bits all will be sampled at a particular time, and this can help to prevent any attacks. Implementation and results. So the proposed puff has been implemented in the LT-SPICE software, which is open source. What are the technology models we have used? We have used predictive technology model from Arizona State University. The 4-bit puff circuitry has been shown earlier. For that, we have performed a Monte Carlo simulation with the gate oxide thickness variation set to 5%. From Monte Carlo simulation, the response bits are sampled and post-processed in MATLAB. The figure here shows the transient response of a single-bit puff cell. The blue color figure indicates the VPC, which is a trapezoidal power clock which has been applied. And the green and the red color waves indicates the response bits. As you can see, if the R is following the VPC, R bar is also tries to follow it, but actually we have limited due to the gate oxide thickness. So we can consider it as a 0, 1 and 0. Next thing we have evaluated is the reliability. As we are proposing the circuit, reliability is an important factor. So for evaluating the reliability for the proposed circuit, we have varied the temperature from -20 to 50 degrees. So we have varied the temperature from -20 to 50 degrees, and we found that the average reliability of our circuit is 99.7. So it can be used everywhere. For evaluating the reliability, we have used the above formula, where HD indicates the Hamming distance, RI is the response bits generated at room temperature, and RI of T indicates the response bits generated at different temperature. Evaluating this, we got the reliability. The next thing is bit error rate. Bit error rate is somewhat indirectly derived from the reliability. Just indicates the number of bit flips in the variation in the temperature. Finally, the energy consumption. We're using this circuit for the portable devices, so the energy consumption should be as low as possible. We have evaluated the energy consumption as I into VDD upon F clock, as this took from the previous research papers. So VDD is nothing but 1.1 volt in our case. F clock is the 100 megahertz. Using that, for various values of load capacitance, energy consumption has been plotted. Finally, we have compared our work with the existing works. Our puff has a uniformity of 41.36. Basically, uniformity indicates the number of ones and zeros generated from your puff. If they are equal to 50%, then we can say your puff is good. And we have also evaluated average reliability. The thing is, our proposed circuit contains 6 transistors. In future, it might be possible people can come up with a new idea so that the number of transistors per bit can be also reduced more. Conclusion. So when compared to the quasi-adiabatic tri-state puff, our circuit has fewer number of transistors per bit, as said earlier. The proposed puff uses 2 CMOS inverters, which can discharge the response bits to ground when disabled. So no retaining, it's not a memory. We'll disable the puff, the response bits are discharged, you cannot even track it. As said earlier, the proposed puff is designed and simulated in LT-SPICE using predictive technology model from Arizona State University. Final thing is the proposed puff has an average reliability of 99.7. These are some of the references used in my study. Thank you.
Thank you. Any questions, guys? Questions from anyone?
I'm talking about the duration of evaluate phase for 256-bit.
Okay.
The time calculation on that, because enrollment is a main important concept.
So you're saying the VPC, the power clock, the evaluate period. Okay. Because it should not be much larger. If it is too larger, the current consumption will be increased. So it should be limited between minimum and the maximum. Yes. We've not gone through very deep about it. It's just an accurate simulation.
Thank you. Yeah, thank you, thank you.
Can you go to the last slide?
Conclusion.
The simulation, what tool is this?
It's LT Spice,
It's a Monte
open
Carlo
source.
kind of simulator or just a
No,
regular
no, no.
Spice
Monte
simulation?
Carlo simulation is just a tool used in LT Spice. That's it.
So,
So LT Spice is
and the
where we have
technology is
designed the
what?
circuit.
What technology is this?
It's 45 nanometer from Arizona State University, predictive technology model,
Okay, it's a, okay, I see.
PTM.
So was there any work in trying to lay this out, or it's just more of a
So
schematic? Did you physically lay out
No, no, no. It's just simulation. That's it.
simulation thing? Okay. Okay. Any other questions from judges?
Yeah, one question.
Yes, sir.
So the concept of these two, using these two CMOS inverters.
Yes.
So is this an original idea or was this actually referred to some other paper?
No, it was an original idea. Actually, previously the authors had an idea that using CMOS inverters we can use, but they deployed additional transistors, so the complexity is pretty much.
Did you look into the challenge when it has noise in the signal?
No, no, no. We haven't looked at it.
Okay, and another typical problem that you see with PUFs is like
Yes.
machine ML attacks. ML attacks.
Machine learning attacks, okay.
So did you do anything?
No, actually it is a weak puff. There is a maximum possibility. We don't use it for device authentication. We just use it for the key generation. So there is a possibility of machine learning attacks if the challenge response pairs are minimum.
Okay, thanks a lot. Thanks for the lovely presentation. Thank you. Okay, the next presentation is on physical implementation of FUSA features. FUSA is functional safety in automotive chips. This by Shashikiran and Badri. The next presentation is on physical implementation of FUSA features. FUSA is functional safety in automotive chips. This by Shashikiran and Badri.
Hello everyone. My name is Badri Ramasubramanian, and this is my colleague Shashikiran Srinivasa, and we work at Marvel Semiconductors as physical designers in the Central Engineering Group. Today we'll be presenting physical implementation of functional safety features in automotive chips. A brief look at the agenda and then we'll dive right into the topic. So we'll give you all a brief overview at a very high level of what functional safety is, the standards, and we'll tell you what we'll cover today. Next we'll go over the problem statement and the methodology, which is basically the flow that we put together to accomplish our tasks. Of course, we'll share results on some of our test cases, and then we'll conclude with findings, which will give you an insight into where our presentation sits in this automotive compliance system. And we also hope to provide everyone here with an insight into what physical design teams will need to look at for successful auto compliance. Finally, we'll open it up for Q&A in case you have any questions, comments, or feedback. Yeah. So what is functional safety? Put simply, functional safety is the practice of ensuring systems operate safely under all conditions. And given that there are humans either behind the wheels or outside that the system could potentially impact, any malfunction in the system could have very bad consequences. And so functional safety is of paramount importance in automotive chips. Consequently, the ISO came up with standards that design houses and the ecosystem at large would need to adhere to. And the standard is called Automotive Safety Integrity Level, or ASIL. And they actually go from A to D depending on the nature of the chips, like an Ethernet chip or a PHY chip or an airbag safety controller or a full-blown self-driving car. Likewise, the implausibility of failure arguments and reviews with your external safety inspectors is also going to have the highest levels of thoroughness and rigor as you go from A to D. Now, this ASIL in itself is a big topic that spans several different levels of abstraction, from architecture to front-end to DFT. We won't be covering all of that. We will just focus on the physical design portion of it today. And really, there are two key aspects to physical design. One is redundancy and the other is robustness. Redundancy can be done at the module level or all the way at the chip level, where the chip itself is instantiated twice, right? And robustness would mean any and every PD methodology that directly impacts silicon robustness. So things like timing margins, EM, aging, immunity to process variation, etc. Now, we won't be covering the robustness part today, and the reason being that it really depends on the mission profile of the chip in the field, and also the operating temperature, which is subject to various different factors. And the robustness aspect can be dealt with in a mature design house with potential silicon learning, so that you can tweak the existing methodologies to get greater silicon robustness for metrics like reliability and timing. We will just focus on the redundancy part today, and on the physical design aspect of it. So next up, the problem statement. The problem statement is quite simple actually, and that is to achieve true independence between the redundant elements for all of the different safety schemes. Now, we won't be covering the safety schemes in great detail today, but I will just touch upon it so that the subsequent slides make more sense. So we'll cover 3 safety schemes. The first is dual core lockstep, which is basically redundancy at the modular level, along with some comparator logic. So you have a primary core and a redundant core along with the comparator logic. The next is triple modular redundancy, which is redundancy at the register level, along with voter logic, which provides both detection and correction. And finally, we have fault and parity lines, or interrupt and parity lines. There are a lot of parity schemes in our safety designs that we use, but we will cover a simple case of an inverse parity line that crosses clock domains. And again, the problem statement is to achieve true independence between these redundant elements such that if one fails, the other one can kick on and function successfully. So here we'll discuss the techniques to achieve true independence. There are a lot of techniques. We won't be covering all of that today. We will cover what we can share and mostly what our methodology allows for. For DCLS, we do physical separation, which enables us to do clock isolation and route isolation. And the reason for physical separation is quite simple. We want independence from effects due to process variation, power integrity, /thermal, /IR, which would otherwise be a problem if both modules were, say, sitting on top of each other or in highly congested regions. The reason for clock isolation is again simple. If we reduce the common clock tree area, the probability of a defect in the common clock tree affecting both cores comes down significantly. Route isolation, the nets in the DCLS cores are extremely safety critical, such that we want to protect them. So we don't want any crosstalk from the outside world or from the redundant cores on the primary. And we have some associated routing rules which we've implemented. For TMR, again, we do physical and clock isolation. The reason for physical separation is we virtually want to eliminate the possibility of a soft error event corrupting all 3 registers or bits at the same time. This concept itself is pretty similar to what happens in the memories with the interleaving of the bits. Clock isolation, it is important to note we only do it at the leaf level. And finally, for the fault and parity lines, which crosses clock domains, we want to delay match them such that the arrival times to the synchronizers are within a certain window, such that the probability of valid data out of the synchronizers in the same cycle increases. There are a lot of schemes in front end to ensure that valid data is received, like handshaking, and maybe you can wait for a couple of states to make sure that valid data is indeed read out of a synchronizer. But here in physical design, we want to delay match them such that we increase the probability of getting the data in the same cycle, valid data in the same cycle, so that there is no mismatch. Now my colleague Shashi will cover the...
Okay, thanks Badri for the detailed insights on the FUSA concepts. Now let's see PD flow or methodology for FUSA implementation in automotive chips. And implementation and checkers will be part of this methodology. Clock isolation, physical separation, and the route isolation check will be performed for the functionally redundant modules, and physical separation and the clock isolation check will be performed for the replicated register. We get a safety spec from the front-end team so that we extract the relevant information that is required for the PD safety flow. Next, in the synthesis, this is the stage where we start implementing the FUSA logic. And during synthesis step, we preserve all the DCLS module that are required for the functional safety implementation. And we pass on the safety file to the PNR step for the implementation. During pre-placement step, we insert FUSA implementation scripts and the execution happens at the corresponding step. And checkers will be run after appropriate step. Say suppose physical separation check will be run after the placement, clock isolation check will be run after the CTS, and the route isolation check will be run after the route step. And finally, after PNR sign-off step, we make sure we run all the checkers so that there are no escapes in the violation even after implementing the ECO. Next, we have results. The first image depicts the visual inspection of physical separation of the DCLS module, wherein the primary core and the redundant core are physically isolated or separated by the user-defined value. The second image represents the logical view of the clock tree debugger, where each sequential cells from a DCLS module will be driven by a unique anchor buffer. These unique anchor buffer should either drive primary or redundant module sequential cells, and it should not drive both primary and redundant module sequential cells. And the buffers which are highlighted in circles, those are the unique anchor buffers. Next, we have reports which get dumped as part of this methodology. The first report is the DCLS physical separation report, indicating the physical spacing status between the primary group and the redundant group. The second report is the clock isolation report, where each unique anchor buffer should drive either primary or redundant module sequential cell. Next, we have a route isolation report saying we get a count of nets which are following the route isolation rules and a count of nets which are not following the route isolation rules. Next, move on to the plots. The first plot is the common clock tree defect density, wherein the probability of the defect in the clock tree, where for one of the DCLS instance, after achieving all the isolation, it has come down to 28% in the primary core and 43% in the redundant core respectively. So it directly affects the silicon robustness. And the second plot represents the crosstalk interference, wherein the y-axis, these are the set of modules that we used for the crosstalk interference analysis, and the y-axis indicates the violation percentage, which is the representative of the nets in one of the core, which is aggressing the other core nets. And from this plot, we can clearly see that violation has significantly come down, and when compared to the baseline run. And even though after in DCLS run also we see the violation is very minimum when compared to the non-DCLS run, and we reiterate this process and we make sure that we approach for the architects and we understand, we try to make sure there are any changes that needs to be done, and we'll try to fix this violation as well. Next, likewise we dump reports for the TMR implementation as well. That is the clock separation and physical separation and clock isolation report, indicating physical separation and clock isolation status of each TMR flops. Next, similarly, we dump reports for the parity paths as well, where arrival time for the fault path and the parity path should be very similar, and the delay difference between these two paths should be very minimum. And we also dump reports in order to understand the NDR route rules as well. Next presentation will be continued by Badri.
Sure. So thanks, Shashi. So I just want to highlight that the results that Shashi went over. So for auto compliance, it is all about augmenting your implausibility of failure with your safety inspectors. So whatever is done in physical design, we cannot just look at visual inspection for a few modules and say we are done. So, and that is the reason why we have very detailed checkers, which are text reports, and also we dump out a lot of plots to substantiate our arguments that there is really no cause for concern. So I'll conclude with this finding slide. Like I said in the beginning, it will give you an overview of where our presentation sits in this compliance system. Really, this process is well laid out for front-end and DFT with this FMEDA process, where you can compute single-point failure metric and latent point failure metric. And some of you may be aware of that. But for physical design, it is still a gray area, and there is really no process that is laid out. So I just want to leave you all with 3 pillars that physical design teams need to look into. The first is guidelines, where we have ISO, IP, and tool. ISO has an interesting chapter called Guidelines for Semiconductors, which has some excellent points for physical design. IP, if you're using safety compliant IPs, you will need to read through your safety and design for failure analysis manuals to understand in detail what the physical design / even DFT requirements are, which may impact physical design. Tool, last but not the least, it needs to be ISO certified. I'm not going to mention any tool here per se, but we have seen functional safety manuals, and you will need to read through them as well. Next is design methodology. Redundancy is what we covered today. Robustness, again, any and every PD methodology that impacts silicon robustness, like timing margins, EM, IR, latch-up, DFM considerations. Finally, we have quality management, which is as important as the other two aspects. Every release needs to be tagged with comments added and traceability enabled such that if there is an aberration downstream, you need to be able to go back and reproduce the data from a checkpoint. So 1 and 2, design release mechanisms and data reproducibility are tightly knit and go together. Documentation is very important for any chip development process, more so for automotive chips. Physical design teams would also need to understand what fails they are addressing, whether it is random or a systematic or a common cause fail. And then they would need to figure out whether they're going to go for a qualitative or a quantitative analysis. Now, what Shashi described with the results, where he went over the checkers and the plots, directly ties into this point. And where you cannot go quantitative, you have to go qualitative, which means verbal reasoning to support your implausibility of failure arguments with your safety inspectors. And finally, obviously, it goes without saying, this needs to be periodically reviewed with a methodology team, maybe with even an internal safety methodology team before you go to your external safety inspectors. And we'll conclude by saying that we implemented a very robust mechanism to implement functional safety features in the PNR side or physical design side. And we had very detailed checkers to validate rule adherence through the flows. One thing I want to stress is that we didn't see any undue impact to the QR metrics. We were able to break even when it comes to metrics like timing and power, such that it did not add to our cycles. We'd like to thank, so a big shout out to Anup, who helped us from the vendor side, Cadence. We had excellent discussions with him. And to our colleagues, Rahul, Atul, Pavan, Arun, and Ronak.
We're talking about clock isolation. That means you have to effectively manage your point of divergence, right? That's how we are achieving that isolation. So when you're designing itself, you're making sure that divergence point is redundant, is different, and normal mean logic is a different logic.
Correct.
That's the only thing.
That's right.
Okay.
That's right. But there are certain limitations as to where we can diverge. We try to do it without giving too much. There are different points at which you can diverge. You can either diverge from the PLL, or you can do it inside a partition level or a subsystem level, or inside a PNR block level. So we see what we can do and then diverge accordingly. Like I mentioned, whatever we do, we need to directly compute a reduction in the probability of failure. So at what point you diverge will determine that. And we need to be comfortable with a certain number.
Yeah. And how are managing the non-common path? See, if you want to get low minimum levels, right, that's how you get a OC aware, right, in the path. So are you using a normal CTS approach, or are you using a mesh approach, CTS mesh approach there?
Actually, this flows that we put together support both. We are able to diverge with both mesh style structures as well as conventional CTS style structures.
But conventional, are you able to get the level control there? If you're going to
so it depends. I know this question perhaps is asked because your concern is probably with respect to timing, right? Like if you...
Not just timing, but you're saying that the OCV has to be managed, right?
Right.
We manage the OC by making the POD as max as possible. But
Right.
again, there's a point with a non-common path. There, you're giving it to the tools to work on that one.
I understand. So there may be cases where the frequency is a little bit unmanageable, where we have to fine tune and then reduce the OCV by certain techniques. But by and large, we've seen pretty much good QOR, and we haven't had the need to worry about the uncommon path as well.
On which library you have done this? On which process? On library?
Sorry?
On which process? Which process?
That's something we cannot
Reveal.
Yeah.
Okay. Thank you.
Sure.
Yeah, thanks for the presentation. So
Sure.
I think there are 2-3 aspects to it. One is basically to understand which were the pieces that belong to the FUSA logic, implementing them in a way that the problems do not happen in the first place. Secondly, using the features of the tool which you are using. And thirdly, maybe putting some scripts into place to implement as well as to check whatever you have implemented.
Correct.
Now, how much of it was manual, how much of it was tool-driven, how much of it was script-driven? Can you give a ratio of these three?
So I cannot give you a percentage number, but what I would say is EDA tools are looking at building something like what we just presented.
Right.
Not all of what we presented today is
Right.
there as a capability in the tool. A lot of it was done in-house. But
Right.
tools are looking
Majority was in-house.
majority was in-house.
Right. That is what I just wanted to confirm.
Right.
Thank you.
But EDA vendors are looking at building something like this for robustness.
Understood.
Yes.
Understood. Thank you very much.
Sure.
Sorry, we just came at the end of the session
Sure.
almost,
Yeah.
but we could able to understand the crux of your presentation basically. You're talking basically from the physical implementation aspect. When we say physical implementation, actually there are a lot of incoming components. A lot of incoming components from logic, I/O, memory, and all of that. How do you assure that these are basically FUSA standard or maybe ISO 26262 per se? How do you make sure that? Are there any instructions given upfront to the components team that they need to take care of it, or there are certain things the component teams have to do and then basically pass it on to SOC team?
So we didn't cover the whole FUSA process compliance in detail today. We just covered a set aspect of redundancy and what it means for physical design. But yes, for example, you spoke about memories. They need to have like a certain ECC scheme built in to protect the memories. So they do have a certain process that they need to adhere to. And the other components like GPIOs, for example, and in fact even all the way from pads to the bumps. It is all about, so there is, in functional safety, there is a design for failure analysis review method, right? Where every, from bumps all the way to the transistor level, you look for breakpoints and then review each one of them separately and then make sure that they're functional safety compliant. And there you support the implausibility of failure arguments, right? So every breakpoint, like for example, memories, bumps, pads, down to the transistor level will need to be looked at. We didn't cover that part today, basically.
Yeah. No, just curious to understand, like, how do you make sure that incoming IPs are basically FUSA compliant?
Oh, that is straightforward. The reason is because I did have a point on the IPs. Any IP that you use, right? If you're using it in your safety schemes, in your safety designs, it needs to be safety compliant with a seal from your third-party safety inspector. Otherwise, you will not be using them. They do come with a safety manual or a design for failure analysis manual, which will give you detailed guidelines and recommendations on what to do, what kind of ECC to implement for memories, for example, right? Whether you need to, in fact, even separate your DFT logic.
Yeah, basically we'll get a safety spec before we start implementing at the PD level. What can be physically implemented? What logic or what IPs basically?
Okay.
Yeah, you will need to read through the safety manuals for the IPs. Okay. That's the only way.
Yeah, thanks.
Yeah.
And one last question. I just noticed that you had given a credit to Cadence. So can you just elaborate what were the FUSA compliant tools basically were involved?
This is still a work in progress from all sides, right? So without going into too much of detail, like I said, majority was built in-house, but there are some powerful capabilities that can you use to achieve what we just presented. It may not be a FUSA feature as such, but these are just inbuilt powerful features in the tool to accomplish what we just presented today, right? But you can talk to the vendors as well to see what they have.
Yeah, I have a question. Thanks for the presentation. I missed the first part of it. Can you please share more details on clock isolation? Is it a dedicated clock to FUSA logic or where we call it isolation?
You can think of it as bifurcating at a certain point after the PLL, right? We just have one PLL and then at a certain point downstream and you determine at what point you want to bifurcate, right? You can sit with the architects perhaps, right? And they will tell you what is feasible and what is not feasible. Because once you bifurcate, you also need to think about clock monitoring, right? So it is not two separate clock routes. It is at some point bifurcating after.
So when you're calling it clock isolation, is it like, are you stopping the clock or you're separating the clock?
Separating the clock. Separating the clock, but not at the root, somewhere downstream.
So you have additional logic to separate the clock and control it that comes from design?
Yes, some of it comes from design, some of it we just take care of it in the PD side.
So I just want to know what is that you take care in PD to isolate?
So we determine at what point we need to isolate and then basically bifurcate and build our clock tree from there to the two separate cores. The clock monitoring logic or the additional logic that you're talking about comes from design. So you can think of it as an iterative process as well, right, with the design team. Like we determine where we want to bifurcate and then they tell us at what point they can add the additional logic that you're talking about.
So bifurcating means creating a dedicated clock branch? Or
Yes, yes. Basically an anchor buffer which will drive.
The reason is that
Yeah,
at
I don't know
what
whether you
level,
saw the. I don't know
will
whether you saw the.
yeah, maybe I
Maybe we
missed the
can.
first part.
Yeah.
I'll
Sure.
connect
We'll be
on-
happy to share the slides as well. Yeah.
Yeah, sure. Thank you.
I think the branching might happen at any point in the level. The only thing is, it should not feed clock to the redundant module or the logic, whatever it is sitting. It's not at a particular place where it can bifurcate. It can bifurcate at any point. The only thing is, it should not feed clock to the redundant sequential cells.
Yeah, and where you bifurcate, you may want to run it by your architects just to make sure they're okay with that.
So, since you're using redundancy and all that, I'm assuming it's either C or D. I know you don't have to tell me, but so do you guys have a logic-based kind of structure also? Yes,
we do.
So, how do you tie that into the physical implementation? Because
So we haven't covered the DFT aspects.
but you,
yeah, we do have a.
Okay, I'll talk to you offline.
Sure.
Do you include SI as well into your analysis?
SI signal integrity, crosstalk. You mean? Yeah, I mean our sign-off timing runs are all crosstalk.
So that's pre and post. If you do that and compare, or
Correct. So the crosstalk interference plot you saw, right? Like for example.
so that's pre and post.
That is pre and post, exactly. We ideally want zero crosstalk.
Yeah, I think this is the one, the below plot.
Okay, thank you guys. Thank a lovely presentation, and thanks for patiently answering all the questions. Guys, for the presenters, just please stick around. We have the mementos, but we decided to give it at the end of the session so that you don't run off right after your presentation. Right. So thank you so much.
Thank you.
Mission is design and optimization of FinFETs using machine learning methods. This Hemlata, are you Hemlata? Okay, Hemlata, Arvindraj, Balmurugan, Suguna, and Kavitanjali. So two of you are presenting? Okay, please go ahead. Thank you.
Very good afternoon, everyone. Myself, Hemalata, and he's my colleague, Kavitanjali. Today we are going to see about design and optimization of FinFETs using machine learning methods. Okay, these are the agendas we are going to see about today. And overview of my presentation, why we go for an optimization. In every environment like education, health, and other application, we need to make a decision when we are handling huge number of data. We need to make a decision about that, so that we are using a multi-objective optimization combined with machine learning. In that multi-objective optimization, we need to collect the data first, then we need to process the data, and we need to interpret the data. After that, we need to apply a optimization algorithm to that. After the optimization algorithm, we need to take a decision making on that. So that by applying a machine learning algorithm into the multi-objective optimization, we can able to minimize the production time,
and also it deals with a real-time problem, and it is very cost efficient also, and it can solve multiple solutions using this.
And moving towards the problem statement, in today's environment, we are moving towards the short channel devices. And so when we go for a short channel problem, Moore's law states that for every 18 months, transistor on a chip doubles. So to enable the Moore's law, we need to increase the transistors in the chip, so that when we increase the transistor in the chip, chip consumes more power and it leads to heat problem. So we need a back-end cooling system to reduce the heat system, so that we moving into a multi-gate technology. When we using this multi-gate technology into today's technology growth, we can able to use these multi-gates in biosensing and high density SRAM and ultra low leakage power system. And scope is when we are moving beyond the conventional structure, we can able to reduce the operating voltage of the device, and we are moving into the technology node is up to 3 nanometer, and we can able to improve the switching speed of the device, and performance of the devices gets increased up to 35%, and power of the device gets reduced up to 50%. These are the methodology used in our work. Here I have shown the design framework of multi-objective optimization. In this, we have to select the design variables first. Then we need to formulate the objective function for the chosen design variables. Then we need to set a variable bound for the design parameters chosen, and we need to select the optimization algorithm which are suitable for the design problem we have chosen. Final one is obtaining the result for that optimization problem. That figure is shown for this algorithm I have chosen. Here I have chosen a NSDA 3 algorithm for the multi-objective optimization problem. Why I have chosen this? These are the most efficient algorithm in multi-objective optimization. In that, we need to set a reference point first, and then we need to generate a initial population, that is a parent population. From that random population, we need to evaluate for the child population. We need to generate the child population until the conversion criteria is meet. And these are the results I have obtained for this multi-objective optimization problem. And first graph shows the Pareto friend. Pareto friend is the one of the performance measure in a multi-objective optimization. And here I have chosen two objective as my problem. First one is a scaling length. Another one is the IDBL current. In a multi-objective optimization problem, between two objective functions, there is a trade-off between that. If you want to compromise between these two objectives, if you want to design a better scaling length, we need to compromise on the IDBL effect. Or else, if you want to be good to IDBL effect, we need to compromise on the scaling length. And for that problem, we have obtained a scaling length of 4.9 nanometer. I have obtained the highest IDBL current of 6.5 into 10 to the power minus 7 ampere. And when we increasing the scaling length, IDBL gets reduced. We need to compromise one objective function in order to meet the other one is better. Second one is the probability plot for the parameters used for the optimization. And what are the parameters used in this multi-objective optimization? This probability plot will give the how efficient the parameters are used in this work, and how frequently the parameters are used in this work. From that graph, you can see that the T-ox of 11.5 nanometer is frequently used, and W fin without the fin is 10 nanometer is frequently used. From that T-ox of 2.5 nanometer, we can able to achieve the highest IDBL of 6.5 into 10 to the power minus 7 ampere, and the width of the fin of 2.2 nanometer, we can able to get the highest current. These are the result for the optimization problem we are chosen. These two graphs are for analyzing the performance of the optimization algorithm. First one is for the average spread. For a good optimization problem, there is a spread between the objective function is lies between 0 to 1. For that problem, we have obtained the average spread of 0.416. And the second graph indicates the performance indicator, that is hyper volume versus generation. This graph indicates that how much generation our algorithms go for. Here we have obtained approximately of 1000 generation for our optimization problem. And these are the results for a machine learning program. We have chosen 1000 data set collected for the chosen device. From the 1000 data set, 700 data are used for the used to train the algorithm, and 300 are used for test the algorithm. For training data set, the model is well fitted for the linear regression problem, and 300 data set are used for the test problem, and we have obtained a RMSE value of 1.146 into 10 to the power 5. And these are the findings of our work. By using the multi-objective optimization problem, we can able to predict the decision making very quick, and we can able to mimic the TCAD process for each device, and it quite efficient, and this FinFET device will meet the IRDS technology node for a future technology growth. These are the conclusions for our work. Here we have obtained the machine learning model for a FinFET device, and we have obtained a global optimization gradient-free algorithm for the FinFET technology. And the proposed move-based ML algorithm will give a efficient and cost-effective product design.
You have told that you have used the data sets. Whether it is any standard data sets which is available?
No, we are creating the data set from using a TCAD simulation.
Okay, it's some benchmark. It is from some benchmark circuits, or?
No, we are creating for our FinFET device.
Oh, okay. What are the parameters that you have used for training?
Training the data set.
Yeah.
Device parameters like width of the fin, height of the fin, thickness of the silicon channel. Those are the parameters we have trained for that.
Okay, thank you.
Okay, did you take into account like the variability of your parameters?
Variability of a parameters. No, sir, we are not taking into that.
Because and why do you call it like ML? I didn't really understand where is the ML part coming in.
Sir, here the multi-objective wrapped with ML.
So what is ML there?
ML is training by using the device parameters.
No, what is that training machine learning algorithm that you did you create something, or like is it?
I have used a linear regression problem for that.
So you have designed an algorithm and got a model. Have you compared it with your normal spectral simulations? How much is the error percentage you are seeing there?
No, sir, we are now working on this only. We are not compared with any other.
Yeah, because when once you implement in the SPICE, you get how much error percentage you have. Then only.
What, sir?
When you have built a model here, right? But later on, have you compared it with any of the actual SPICE simulations?
In future, I will try to compare with the existing algorithms.
Okay.
Right, thank you. Thanks a lot. Presentation is a frequency optimized linear scalable architecture for CNN interface on FPGAs. This is Nandita Rao, Shubhayu Das, and Sharat Sinha.
Good afternoon, everyone. So I'm Shubhayu Das from IIIT Bangalore. I'm an undergraduate student, and I'm here to present our work on frequency optimization of a scalable architecture, and I'll get to why scalable for CNN inference and FPGAs. And I have done this work under the guidance of Professor Nandita Rao from IIIT Bangalore and Professor Sharat Sinha from IIT Goa. So let me walk you through what we have done. In this work, we are going to look at architectural modifications. The algorithm is nothing new because CNN inference has been around for decades of very intense research from 2012 especially, and there have been architectures coming up even before that for convolution. So the architecture by itself is nothing new, but we are going to look at how we have mapped it better onto certain FPGAs. And we want to use a very simple architecture. Why do we want to make it simple? Because we are looking at a very small FPGAs, which are cheap, and I'll get to why cheap as opposed to big FPGAs that AMD Xilinx has or Intel has. And we compare our improved design. We'll see what is the improvement against certain baselines, other works which have been published in other conferences. So in this work, in this part of the work rather, which I'm presenting here, we're going to limit ourselves to one image kernel convolution. This is not one layer of a CNN. This is not an entire CNN because we are working with very resource constrained devices. We are using low-cost FPGAs, definitely, because we want to use these widely. We don't want a very expensive FPGA that you will be afraid to put on a drone, for example. You want a small FPGA, and we want to see is it feasible to do it on a low-cost FPGA. And for this application, we have not used any off-chip resources like DRAM, so DDR memory as an example. We do have the capability now to do it. I'm not presenting the data in this particular presentation. Okay, so moving on to the overall architecture. I'm sorry to the people who are sitting this side, this is not really visible. But in general, we have storage, we have data buffers which contain the data which needs to be fed to the CNN network, or in our case, one image kernel convolution. We have the kernels, we have the data which is going to come in. We have two memory movement structures. One is called the kernel unit, which I'll explain. And I have a linear FIFO buffer. This is going to contain the data. So whatever data, or let's take an example of an image. We want to do the convolution of an image with a filter kernel. We're going to put the image into the linear FIFO buffer. We're going to look at the structure of that. And we're going to put the kernel or kernels, multiple are supported as well, into the kernel unit. This is the data handling so far. And then we have the processing, which is done by multipliers and adders. So we have MAC operations, of course. And we're going to look at what architectures of multipliers and adders can be inferred based on the way we implement it in the tools. So for our purposes, we have used only Xilinx tools, or AMD Xilinx tools now. And we have used the toolchain called Vivado from Xilinx to implement all our designs. So let's look at the data movement that we have used in our work. We have a kernel unit, which is essentially just going to take the data, rearrange all the kernels to pack it onto a bus whose width is completely parameterized, and we can move the data into the control logic. Why do we want to parameterize something so simple? Because the reason is these kernels need not go to one single convolution. There might be multiple kernels that you want to convolve with multiple images in the future. And if you keep increasing the width, you will run into timing issues in an FPGA, especially when you're looking at a resource-constrained FPGA, which might not have too many clock lines to feed to multiple CLBs, configurable logic blocks in Xilinx terminology. So we want to keep that parameterized so that we don't run into timing skew issues. And at the same time, we want to make it wide enough to feed in enough kernels at the, so that we don't choke ourselves transmitting kernels. In this example, we have showed how a 3x3 kernel would move, and we have showed how 3 kernels would be packaged as an example. If we have more, we can of course transfer more. Okay, and so before we look at the results, these are just crammed into slide limits. This is the linear FIFO buffer structure where the image data, the incoming data would be packed. So for our applications, we have used something called block RAM in Xilinx terminology. This is SRAM, which is present inside the fabric of the FPGA. And we have a configurable width data bus, which is carrying the data into a linear structure. Why a linear structure? So we want data to be streamed in, not just from internal storages, but later on also from external storages. And if we do something fancy where we have data coming in irregularly, it would be hard to organize it, first of all. Second thing is data reuse becomes harder. So let me just walk you through how this structure works, and then we can look at why this structure and why not something more exotic. So in this structure, we have data coming in from the last element, which is probably better visible here. And this is just a simple FIFO structure. FIFOs are 60 years old. We have been using them forever. But if we fold the FIFO in a very specific way, we can actually move the data around and perform the convolution on elements. So every clock cycle, I would shift the data as shown by the arrows in the bottom diagram. And at the same time, if I use this particular subset of elements, 3x3 in this particular case, I've shown a 3x3 kernel example. Depending on the size of the kernel, we can change the size of our linear FIFO buffer, as we are calling it, and we can perform the convolution. What am I gaining? I'm moving in data, and at the same time, I'm doing convolution in the same clock cycle. And the data which is coming out of here can either be discarded, or it could be fed into another structure, another LFB, to perform another convolution with more kernels. Right? So achieving two things with the same structure. This is a simplistic structure. This is not new. This has been around for a long while, but we are using this particular structure. If the operation is working is not clear, maybe we can take it up afterwards. I'm available in the conference. Let's look at some of the results. So a FIFO structure can basic things, it can be mapped in several ways. We have serial in, serial out. We have parallel in, serial out. But what happens when you try to put it on an FPGA? So when you do a serial in, serial out structure, in Xilinx FPGAs, there is certain type of memory called LUT RAMs, lookup table RAMs, which are comprised using the lookup tables in their CLBs. CLB is configurable logic block, the fundamental block in their FPGAs. And that structure is very resource efficient. So we can, LUT RAMs are not typically used for other things. We can use them for storage, but in our application, we did not. We are only using LUT RAMs to implement our FIFO structure. And since LUT RAMs are available in good enough quantities, we can actually replicate these structures several times to implement multiple image kernel convolutions at the same time. And we'll see an example of that. The alternative way is to use a parallel in serial out structure. Parallel in serial out structure, as expected, will not incur a input latency. So what do I mean by input latency? After power on or after a reset, when I'm starting, I need to fill in the structure from the end to the beginning. And if I don't do that, I cannot start producing an output. But in a parallel in serial out structure like I've shown here, you can move in multiple data in at once, obviously. So that speeds up the operation and decreases the latency that we incur. But at what cost? The cost or the problem that we face is that the LUT RAM structure breaks down. The tool Xilinx Vivado does not identify or cannot map the parallel in serial out structure onto LUT RAMs because you have multiple accesses to individual elements, and LUT RAMs don't have that much input bandwidth and output bandwidth to support parallel operations. So, and we'll look at results to quantify this, of course. So that is one thing to do with the LFB, and this is, if we go back, we see that this is just the data movement part. We also have the arithmetic part, which is doing the actual computation, of course. So we have got data in the right way. We have got the kernels. We have got our data in the LFB. What we want to do next is to do the multiplications and do the additions. A very naive, simplistic implementation would, it would be like A into B plus C, or if I'm being more specific, A1 into B1 plus C1. This whole thing is again accumulated with A2 into B2 plus C2, and so on and so forth, which is how convolution works. And you would do it for K square, where our kernel is K by K. And that would in effect give us a latency which is huge, because what the tool does is it will cascade all of these blocks. It will put them in a combinational path, which of course reduces your clock period because you have a long delay now between two flops. So that latency we quantified and we found in the tool to be K square into alpha, where alpha is the delay of a DSP block. What is the DSP block doing? It's doing the MAC operation, multiplication and accumulation. A slightly smarter implementation, which is shown in this figure, would of course do all the multiplications in parallel and then use an adder tree to accumulate the results. And this delay can be quantified as the maximum latency between the multipliers, which is done by the DSP blocks in our implementation, and the latency of the adder tree, which is log K square, where K square is the number of additions that you have to do into the delay of each adder. Now, the adders are implemented using an adder 4 block, which is a dedicated hard adder built into the Xilinx CLBs, or you can do it using LUTs. In this case, it uses the LUTs. That's what I've mentioned at the bottom. Sorry again to people who can't see that. And if you want to optimize it more, we want to improve this frequency of operation, we can pipeline the adder as well. And this comes at no great cost because flip-flops are like very common, very like available in large quantities inside the FPGA. So we can actually afford to pipeline our adder tree completely. And this would again reduce the critical path, improve the operation frequency. So that is a CU config, what we are calling CU config 3, where the latency decreases to the latency of one DSP block, which is a hard IP inside the Xilinx FPGA, and the latency of an LUT-based adder. And this is what we have used, and of course it gives the better performance. So these two are the naive implementations where we have cascaded operations happening. Cascaded, the critical path contains all the MAC operations happening in a single clock cycle, not efficient at all. Next, we pipeline the DSPs, but don't pipeline the adder tree. And then we pipeline the adder tree as well. And we look at what happens when we use a parallel in serial out structure and what happens when we use a serial in serial out structure. Tentatively, theoretically speaking, parallel in serial out structure will obviously will do the work in far fewer clock cycles, but at what cost? And that again, we'll see in the results. So these are the schematics, post-implementation schematics. Implementation is after the tool has done place and route. So each of these cells have been mapped onto some resource in the FPGA. And here, if we see the cascaded, we can see the cascaded path highlighted, and this is forming the critical path where we have k-square elements. We have 9 DSP. So each of these blocks is a DSP block, not really visible because the design is big, but yeah, this is the critical path. Whereas once we pipeline it, so we have the red boxes, which are the individual flip-flops, which are pipeline the adders. So the blue boxes are the adder cells, and we have used flip-flops to pipeline the structure. The big boxes are DSPs here, and those are all in parallel to do all the multiplication operations. So we can see that for a 3x3 kernel, we can go from this to that. Of course, that is a smaller screenshot. This looks like a big design. That looks like a small design. It's not. That is just a screenshot of a far smaller block. So this is the overall implementation on the FPGA, and we can see that we have used most of the FPGA. This is an ultra-scale plus architecture device from Xilinx, a very small one at that. It's called the Ultra 96 V1, and we have used most of the FPGA. The pink color are all the DSP blocks. We have used all of them, and we have also gone ahead and used multipliers which don't use the DSP, so that we can utilize more of the FPGA. And so if you look at results, I'll basically point out the interesting results. So parallel in serial out is here, and serial in and serial out is here again. So if you look at the highlighted result, we can see that there's a huge gap between the parallel in serial out and the serial in serial out. And that is because the parallel in serial out architecture gets mapped to more inefficient hardware. It does not use LUT RAMs anymore. It uses flip-flops which are spread over a large area of the chip, which makes the clock reaching to individual components much harder. So we have a increased latency of operation there. We are doing this for an AlexNet kernel, where we have a 9x9 kernel and a 224 x 224 image. And this is comparison with other works. Our design is at the end. We have compared ultra scale plus architecture. We have done our work, implemented our work, tested it in real hardware on an ultra scale plus FPGA. And while gigaflops is not a good comparison in this case, we have achieved comparable results with some other architectures like the Zinc Z045, which is a far larger board, but and far more expensive, but we have achieved better frequency of operation and more operations per second. So these results are questionable. If you do have questions, I'm more than willing to answer. Thank you.
Thank you. Questions from the audience?
So you implemented your design with all the architectures, right? So
this is on a Z board, by the way. We don't have the data for this Ultra Scale Plus device. This is on a different PC board, but yeah.
So, but you are talking about your work is related to on the convolution layer, right?
Yes.
So in VGG16 and AlexNet, LeanNet having the pooling layers, fully connected layers, in ReLU, lot of things will be there. How you handle those things?
So we have not implemented a fully connected layer yet, but we do have pooling. This data is only for a convolution as of now. We do have a pooling layer. So the pooling layer can be actually implemented.
Those results only for convolution layer?
That result is only for convolution, but the exact same architecture can be used for pooling.
Okay.
And if you want to know how, so we already have, let's say we are doing 3x3 pooling, okay, max pool 3. We would look at these 9 elements and we would try to find the maximum, right?
Okay.
If it's visible. When we are doing MAC, we are taking all the things and we are multiplying and adding. When we are doing pooling, we want to look at all of them and compare them.
Yes.
So using the exact same structure, I can implement pooling as well.
So this is for only 3x3 or it can...
Completely scalable. So this is the generalized form.
Okay.
And I have the generalized formula as well. I'm sorry the text is probably not very readable. But we can go K cross K, and we are only limited by the number of DSPs in the FPGA.
Okay. Last slide, can you... The results. So here you used the 16-bit fixed point, right?
Yes.
So you calculated the accuracy?
So like I mentioned again, this is one image kernel convolution.
Okay.
So as a fair comparison, that's why I mentioned that those gigaflops is not the only metric. If you're looking at the accuracy, what would be a fair comparison is if you look at other 16-bit fixed point implementations, right? Because we can assume that the parameters that we're using in our model are the same.
No, I'm not asking about this comparison. Like I'm asking if you're using 16-bit.
Yeah.
So if you're going for the real-time implementation.
We have not implemented an entire model on this yet. We are not there yet.
No, I'm generally asking, like,
Okay.
if you're using the 16-bit to the entire architecture in future, you will take care the accuracy, right? Like, it may be
Yes.
a drop in accuracy. How you will handle this?
So if you're looking at accuracy, right? So the first question comes is that, do we need that accuracy? Where are we trying to use this? Is this a safety critical application where we're using it at? Or is this a relatively casual application, right? And our work definitely does not cover this, but I've read other papers where they do quantization and look at the effects of quantization. And for certain models, I'm sorry, I cannot give you exact details because I don't remember it. But if you go to 16-bit fixed point or if you go to 8-bit fixed point, there is drop in accuracy, definitely, because you have lesser dynamic range. But that drop is not significant. Why is it not significant? Because we are looking at a low power device. We are looking at a tiny device. So that you have to accommodate, right? Because if you want more accuracy, go for a larger device. We literally don't have enough DSPs to, so in Xilinx architecture, DSPs are 18-bit in size. Each DSP can do 18-bit multiplication. If you go to 32-bit, for example, we'll have to use 2 DSPs. Right now, we have 360 DSPs compared to, let's say, 1,500 in the ARIA 10, Intel ARIA 10. 360 DSPs, if we go to 32-bit architecture, we'll only be having 180 effective DSPs. And that is going to limit the overall architecture. So on one side, you have not possible at all on this FPGA. On the other side, you have possible but with reduced accuracy. So it's a trade-off that you have to make. You decide as in an application-specific place that, can I handle this drop?
Okay, the last question.
Yeah.
You use the inference, CNN inference. So
Yes.
you extracted the weights from
A trained model.
A trained model. So which data set you used to train the model, actually?
We have not trained the model here. So we have taken a trained model. And to be honest, if you'll just look at the from an architecture point of view, we want to verify if the convolution is happening properly, right? Okay. That's all we need to do. So we can even generate random numbers, feed them in, and see if we are getting the correct result. How do we generate random numbers? We look at the maximum and the minimum that we need to generate. And we generate random numbers and we tested it with that. If you want to, I have actually tried with the PyTorch trained model for MNIST. We trained it in PyTorch, quantized it to float 16, and took out the weights, put them into this. Okay, not float 16. I think, float 16 in Python, and then manually converted to fixed point 16 using MATLAB. Fed them in, and we have compared the results in a logic analyzer versus the software generated output between layers.
Okay, thank you.
I'll ask something very simple, like, you have this computation, right? Like,
Yeah.
basically you're optimizing the Mac.
Yeah.
So there is a lot of sparsity that comes in, right? How do you deal with sparsity?
Sparsity as in, like we're using only 9, but we have a lot of unused elements, right? The trade-off that we are looking at is data movement versus sparsity here, right? So I can either get in 9 elements in every clock cycle somehow, and I can deal with it, or I can use something like a systolic array, where you have 2D data movement and you're using it on, maybe not almost completely, but you're using a greater chunk of it. What I decided to do was handle the data movement part first, because as of this work, we did not have the data movement coming in, but later works, we have used HICC to get data in from this thing, DDR memory, external DDR memory, feed it in. And what happened was we ran out of memory bandwidth first before we ran out of resources. So in that case, we have enough LUT RAMs. We have enough LUT RAMs even in our simplistic FPGA to handle, like, to tolerate this extra thing. But what happens is the data, you mean like sparse matrices? We don't. This architecture cannot support sparse matrices. So although I'm trying to understand your question better, I have personally not come across CNNs which have sparse matrices. Is that a common phenomenon? Just binarized? Okay. So binarized, if you're looking at BNNs, then I think there are better architectures from NVIDIA, like I think Fin compiler, which generates a much more optimized architecture. Yeah.
In the last comparison slide,
yes.
So you have actually used FPGAs from different process nodes.
These are other works. Yes.
Yeah,
Yes.
other works.
Yes.
Okay. So my question is, like, suppose if you are using the same FPGA, you do not have access to those FPGAs. So that is the reason you cannot do an apple-to-apple comparison.
Yes.
Right? Okay. Yeah.
So as an example, I have the values, that's why I mentioned. So this is a 28 nanometer process. We do have 28 nanometer results from before. This is on a 28 nanometer FPGA. This comparison has been done on the same thing, but this is a smaller FPGA compared to what they have used over there.
Okay. Yeah. So yeah, would it have been better to just use the same process node? I mean, so that the comparison could
Comparison
have
is
been,
fair.
Yeah.
I get that, but the thing is, so two things. One thing is, we have data for 28 nanometer and 16 nanometer, so we can do an apple-to-apple comparison with this if you want to. If you look at this, I think, do I have the gigaflops here? No, I don't. So if you look at the total number of convolutions per cycle effectively, it is of course lesser than the others. But what we have to look at is the size of the FPGA that we're dealing with. And the size of the FPGA is significantly smaller than what is available, what is used by other works prior to this. So I think, yes, it is lesser. So even if you see our result, that is not beating some of these results or that result. If you look at convolutions per cycle, not gigaflops. Even gigaflops is fine, but the actual metric would be convolutions per cycle. And it is not beating, but it is getting there. It's getting somewhere where it can do certain work, but it cannot do it as fast as other things. And the constraint being it's a small FPGA.
Okay.
Thank you.
Thank you guys. Thank you. Good job. Okay, this is the last presentation before the tea break, and we'll take a short break of about 15 minutes post this presentation and come back. So this one is on energy efficient approximate floating point divider. Noor Muhammad, Srihari, Ayesha, and Namrata. So you will present.
Good evening, everyone. So welcome to this presentation where I'm going to present about energy efficient floating point divider design. Again, we have done by using approximate hardware based design mechanism. The core idea is here we have done error versus energy comparison. Based on that, we have implemented this. Let me go through it. Again, the way we have implemented is we have analyzed the entire floating point divider. Okay, if you look at their 24-bit division hardware is needed in the Mantissa, and that's the thing. Typically, conventional implementation will be there, and where we try to brought some kind of approximation at the Mantissa side, such that the error can be we can make it less than 1%. So that's how we have done this one, and the way we have implemented is we implemented 8-bit division hardware at the Mantissa, and the rest of the 16-bit we made it as a subtraction. That gives errors less than 1%. Okay, that's how we achieved this one, and because this kind of things will be used in the error tolerant applications. In the, for example, like image processing, other kind of places we will be using this one. And let's see that the existing implementation. If you look at, we have a sign bit where we'll do the XR, from that we'll get it, and exponent we'll do the subtraction. But when it comes to the Mantissa, where we have to do division of 24-bit division hardware is needed. That's a very big hardware, it consumes more energy. So that's a conventional implementation. And there are reported works, whatever is there, they call it as a floating point approximate divider and configurable approximate divider. These are two works it is reported in the earlier. The way they have done it, they used Mantissa, instead of doing Mantissa division, 24-bit Mantissa division, they have done Mantissa subtraction. Along with, they have added an additional correction hardware, such that they can, means the correction hardware they have used it, such that they can have error is around 6 to 12.5%. That's the error rate they have produced it. So these are two works that is there. Okay, and if you look at the first one of the reported work, that is configurable approximate divider. They are using Mantissa subtraction. That's the one kind of work. Another one is a Mantissa subtraction with lookup based correction. These are two mechanisms they have used it, and which will give the error variation of 5.36 to 12.5. That's the error variation is there when you talk about these two things. But since they are using a lookup hardware, which they are using for the correction mechanism, so the complexity means the additional hardware is used there. So it's definitely saves the energy when compared to the conventional mechanism. But it has a because energy is, when compared to conventional, it is going to be lesser. That's the thing what they have shown that with an error of 5.36 to 12.5. And the another reported work is this one. So where they have used matrix subtraction with correction. Essentially, they have done MUX-based correction mechanism. That's the thing they used in this design, where they also use subtraction here. And the maximum error is they have reported is 6.24, and that's the thing what they got it in this implementation. And they reduced the energy around 25% when compared to the CAD, that is the earlier architecture. So that's the thing what this work has been reported. So now coming to our idea. So what is our idea is we have detailedly analyzed by writing a Python script mimicking the hardware behavior, and we verified that what way of implementation will lead to a lesser results. Okay, and that's the analysis which we have done, and where you can see that the eighth one where subtraction, exponent subtraction and mantissa, where we have a 8-bit division and 16-bit subtraction, that gives the error of 0.78. You can also see that other designs also we have done according to that, where we can have a 4-bit division, 20-bit subtraction, where it's 6% error it gives what error reported work. So it's a kind of trade-off which we have done it. And let's say our objective is to design a hardware which is having a less than 1% error. Let's say 0.78 is acceptable. So in that case, we can adopt this one and we can implement where we have a at mantissa side 8-bit division at the most significant side and 16-bit subtraction at the least significant side. So that's how we have done it, this one. And yeah, this guarantees the 1% error rate. Okay. And so we also tried the implementation in a different ways, where one is, you can see that the fourth one where subtraction with 0.78 it is giving. So we also tried some other logic way of implementation where we are setting all bits at the LSB side as a 1, or setting all alternate bits of 1s and 0s, or eliminating the complete things. So when you analyze that, the error rates has been varying from 0.78 to 6.7, but 100% we can say that when it comes to this one, so we can do that 0.78 we get when you do the exhaustive analysis. Okay, we have done completely exhaustive analysis we have done when it comes to this one, and we have implemented in 45 nanometer technology this one, and where you can see that the conventional energy, if you look at 152.28 picojoules, and when you talk about one of the reported work that is CAD, it is 0.078 picojoules, and FPAD, another one is, it is 0.87, but if you look at the errors, it is going to be higher. You can see that 6%, 12.5% it is there. And as I told that we have 3 proposed approaches what we have taken, 1 and 2, 3. So again, you can see that 0.78 is a subtraction where we use at the LSB side, a 16-bit subtraction, and where 4.62 is something where all bits is all alternatives 1s and 0s that we have used it. And if you look at our energies, whatever implemented result energy, so for approach 3 where we have a 0.59 picojoules, and approach 2 we have 0.098, and then we have a other one is 0.097 picojoules it is there. So that's the results what we got it, and we compare this one with the existing results, where we found that when compared to the FP floating point approximate divider by reference 7, so where we are saving energy of 32.18%, lesser than that one, and that's the energy saving what we have achieved it when it comes to this one. But with error rate of lesser than, that is 0.78, we got this one. And we also implemented on multiple images we have taken, and around 140 images we have taken, and we have done this implementation. Again, image compression we use the implementation, and this what you are seeing, that plot, that is the PSNR values, and it is all acceptable. And what you are seeing, the block one, that is going to be an accurate one, and whatever you are seeing, the red one is the approximate one implementation. Our implementation, we have compared it. Okay, so we are almost matching with the accurate implementation. Okay, so this is the work. Yeah, any questions? Yeah, that's the thing. See, you can see that the errors versus energy. No, no, we have not done that one. We have done only for single precision. So there we have to use some different approach. Yeah, yeah, yes, yes. This technique may not suit to that other technique, 16 point floating point number, other things. We have to work on that. This by using this approach, you can try.
Okay. The approach 1 and approach 3, you are setting either it to 0 or 1. Why the error percentage, shouldn't it be similar? Why is it 6% and 1.39?
So yeah, see, actually you can see that alternatives ones and zeros we are setting. Oh, what you are saying is here. Okay.
1 and 3. 1 and 3.
1 and 3. Okay. No, actually.
I feel like if it is randomized numbers, the output is random number. So the error percentage should be same, right, in both the cases, no?
But here, see, there are, because it's a fractional number, no? Ultimately we are comparing fractional number.
Okay.
So I think this is 0 is something dominating.
Okay. You will take less power with that, right?
Yes, definitely. Again, 0.097.
No, with approach 1 and 3. So have you tried doing a division with 9-bit and replacing it with zeros and ones?
Yeah, yeah, that you can see that 9-bit division and but zeros that we have not tried actually. Okay.
Because just setting the zeros you will save on the power a little bit, right?
Yes. That we have not tried.
Okay.
Yes. Any other questions?
Questions? You guys?
I didn't understand that part, like why you are using PSNR to compare.
So we applied on images and saw that what is the impact actually.
So
because
how many pixels?
Quality.
How many pixels were there? Like in that?
So that's we have taken it's 256 by 256 image size.
And then that's average.
Okay, thank you, Noor. Thank you. Thanks for the presentation. And guys, round of applause, please. Thank you. We'll take a short 20-minute tea break. Be back by 4:10. Okay with you guys? All right. Thank you.
Thank you, Chair. And good evening to everyone. So, the topic of presentation from me today is retention leakage reduction in SRAM using adaptive bias control. You must be aware about the leakage reduction schemes in memories. The very conventional scheme that is used for leakage reduction in memory is, I think the laser pointer is, okay, fine. So can I have a mic then? Mic. I will have to show here. So this is the standard leakage reduction method in memories where a combination of diodes or a single diode is used at the bottom of the memory array. This is the full memory array designed, and a diode is kept in order to block the ground path and saving on the leakage. The application of source bias using N diode or a combination of NP diode used for leakage combinations. Now this approach helps to reduce leakage by providing the source bias to the memories. Now what problem this has? At cross-corner conditions, this scheme basically an evaluation of the earlier scheme where these two devices P and N are compensating for the VT variation in any one of the devices. So if N is higher VT and M1 is of higher VT and M2 is of say lower VT, then the virtual ground will be decided by the M2. Now coming back to the problem, what are the drawbacks of this solution? The minimum retention voltage is limited by the lower leakage PVT condition. See, what we want today, the leakage has increased many folds in the ultra deep submicron technology. And what we could ignore earlier with respect to the leakage, we are no more in a position to do that. We need to minimize the leakage of the SoC when any block is or any memory particular instance is in the standby mode. If you can see, for the particular scheme I demonstrated, the minimum, say, sigma qualification. The red lines are the RNM sigma qualification. So you can see the sigma qualification is limited in SF125. Now the SF is not the largest leakage or maximum leakage condition. The maximum leakage condition is at FF125, where you have still margin. You have 10 sigma qualification, approximately 10 sigma qualification, and then you could have raised at first corner the source bias much more than what you have applied in this configuration. And similarly, if you see under typical condition that is required for many products, the TT25 for handheld applications, the sigma qualification is above 10. So there is a room at this particular process corner that this particular point can go down till 6 sigma and provide you a further reduction in leakage. But you are not able to do that because the stability of your bit cell is limited by this point, the slow fast 125, which you need to take care in the validation space of your design. Coming to the concept of the novelty that is basically I have developed, there is a tracking column where M number of cells are used, SRAM cells. This is my blocking constriction, say maybe a diode. Similarly, an arrangement can be done at the header side also. And this is the actual SRAM, maybe 1 megabit or so, where a diode is used. This is the conventional structure. And this one is the additional structure. This is the control one, and this particular device is introduced here to get control by this tracking mechanism. Now, how this tracking mechanism is working, let me explain that. This is the detailed diagram, the way this is supposed to be implemented. The tracking block will be designed only one for one SoC, and the signals, the control signals for the control of virtual ground level that is basically responsible for the leakage is traveling to all the memory blocks. So this is the actual circuit that we have implemented and validated on silicon. So you can see this is the memory array, this is the tracking column. These are the stack of diodes that are basically representing the logic process. This particular tracking column is representing the SRAM process. In any actual fabrication process, you will always find a deviation between the SRAM and logic process, and that is the reason the tracking mechanism has been developed using a logic process and the combination of SRAM process. And this tracking control signal is taken into this newly introduced tracking arrangement. Now, when there is at cold, suppose at cold or at SF condition, there is the higher virtual ground is there. For the similar higher virtual ground would be represented here at C1, and C1 will provide an additional vent, an additional sink to the virtual ground. And this will lower down the virtual ground at the PVT where the RNM or the stability of the cells is minimum, governed by these diodes. These are the conventional structures. Now coming to the results, you can see the results, the green one with the newer scheme. You can see that the limitation that was imposed at SF125 at this point has been lifted at this value. You can see in terms of sigma, this is more than 2 sigma gain at this point, the weakest point of the design. And this, what is this doing? This is allowing you to introduce more source bias under typical condition. And also this is allowing more source bias at fast 125 conditions. In terms of rail-to-rail voltage, if you see, SF125, earlier the rail-to-rail voltage was this one. And now the rail-to-rail voltage across the memory array is reduced. This is introducing additional stability to the memory array and allowing us to have a higher source bias at TT25 and also at SF125. You can see FF125. So at these points, we are able to reduce leakage to a larger extent while still ensuring the stability of the bit cell at the earlier weakest point. Now, there is another point that is to be considered when designing this, the deviation between the logic and the memory process. The mask set for SRAM and mask set for logic are different, and you can never expect both them to be aligned perfectly. And that is the reason whatever circuit you are designing to control the stability of the SRAM, whether this is a read assist or write assist or retention mechanism, stability mechanism, that has to address to some extent the deviation between SRAM and logic process. And if you see, if the SRAM core goes faster, you will have a higher potential here, reducing its stability. And similarly, a higher potential will appear here in the tracking column. And this tracking column will provide additional vent here. And this will compensate for this deviation in the logic and SRAM process. And vice versa. So all the conditions of loss of stability that could have been arisen due to the difference into SRAM process and the logic process are addressed in a self-aligned manner, in an adaptive manner. And in this way, if you see, we are able to reduce, this is the way we are able to reduce the leakage. The proposed scheme, if you can see, the proposed scheme is able to reduce from the conventional scheme of 1.35, this is picoamps per bit cell. The unit is picoamps per bit cell. Applying the scheme, you can move from 1.35 picoamps per bit cell to 0.33 picoamps per bit cell. And extremely important for particularly for medical applications. For SRMs used in pacemakers, one of the solutions we had earlier developed using this methodology, this circuit arrangement. So you can see the tracker control voltage, the virtual ground and the virtual ground, the prior art, the earlier schemes, how they are varying, and how the variation or the adjustment of the tracker control voltage and virtual ground is allowing you to have a higher rail-to-rail voltage. At SF125, you see the tracker control voltage, you are able to give higher rail-to-rail voltage. With earlier schemes, these were the bars. So significant gain we are observing here, particularly if you see in the GT also, and SF-40, particularly when the VT of the NMOS goes very, very high at the very, very cold conditions, you are able to raise the rail-to-rail up to a very large extent, infusing the stability to the SRM cells. This is the most important gain of this. That is allowing you to use it into, say, multiple handheld applications. So this is the overall summary. The leakage reduction scheme is illustrated. And the scheme is helping to enhance the stability of the SRM cells by increasing the rail-to-rail voltage at low leakage conditions, where you can afford a bit more leakage. And bias at leakage critical PVTs can be increased and minimized, like FF125, high temperature condition, high leaky conditions. You can increase the bias to reduce the further leakage further. Retention Vmin could be lowered from 0.9 volt to 0.81 volt, specific to this technology. In E40 ULB, ultra low power technology we were struggling to go to 0.81 volt under retention and also with bias. For those, this is now enabling this design parameter. Now 2.5x leakage reduction at leakage critical PVT was achieved here, and 5x leakage at typical conditions. The scheme is robust with respect to the possible mismatch between SRAM and logic processes, and this is already silicon validated in 40 nanometer CMOS technology, that is 40 nanometer ULP technology in ST Microelectronics own technology. Thank you. These are the key references. Most of the references are my own work that are being used across industries. Thank you.
So there will be the minimum number of memory cells, right? Per diode or per enable.
Yes. This is a very good question. In fact, number of memory cells in the tracker column and the number of diodes, both needs to be decided based on two factors. The technology you are targeting, and second, the operating Vmin you are targeting. If you are targeting, say, 0.81 in my country, 4 stacks were required. And say, in one column, 512 cells were required. But if you are targeting, say, a Vmin of 0.9 volt or 0.95 volt, the number of diode stacks, maybe that can increase 4 to 5. A number of cells required, that can slightly increase. or if you are targeting further lower voltage, this adjustment can be different. So you have to find out the sensitivity based on the simulations for your own requirements. So this is the conceptual representation. What is important is you need to design the mechanism which is compensating, taking care of both SRAM process as well as logic process.
How about the leakage at 125C? So you have shown 25 picoamps of current at 25C, right? How will it be like at 125C?
125C.
Yeah.
So you can see, this was the specific target at say TT25, but in the earlier graphs you can see the leakage per bit cell with the source bias. You can see that say at say SF125.
So FF125 is the worst case, right, for leakage?
Yes, yes. FF125 is the worst case. So here, this is basically representing the thing. Leakage, red one is the conventional one with scheme, and this one is at SF, this is giving rise to slightly higher one. So at maximum condition, this is almost equivalent under this adjustment. But the main gain here is at TT, because our target was TT. This will not be visible in this scale because this is dominated by the high temperature. That's why we have made this plot so as to make it visible. So when you want to design at a higher temperature, the ratios, the number of the tracking cells and this adjustment has to be different in order to take care of the 125C. But usually at 125C, that is required for the processors, usually for processors that are required.
Okay, so this is for a different application for a different temperature targets.
This is for low power microcontrollers.
Okay. And to have an active write into the memory cell, right? Will it be done without by bypassing the diode or?
Yes, yes. If you see this structure, there is an enable signal. Okay. So when memory is going to sleep or the standby mode with enable 0, then only this whole thing is working. Otherwise, this is at ground potential that is must for the normal operation of the memory, read-write.
For each application, then you're saying it's like you need to optimize it, right?
Yes, the tracker.
Yeah.
The tracker, this one and this one, you have to optimize, you have to design this where you actually want the minimum leakage.
Okay, does the process technology come into picture in your
process technology? Basically, scheme is independent of process technology, but the optimization has to be done with respect to every technology.
So one question. So generally the SRAMs comes as a hard macro, right? So in this case, how the memory, like generator would actually use this particular method to change the tracking column, that sequencing. So how does it work? Is it already in production or?
This is being used in ST.
Okay.
So the already hard IP, hard macro, what you are getting from the vendors or from the fab, that memory cannot use this scheme.
Mm-hmm. Yeah.
So that's why in ST, we have, say, internally designing such more than more concept under this more than more concepts, where existing technologies we are optimizing better for performances and all.
Right.
So these are dedicated developments.
Okay, yeah, got it.
So in one of the slide you showed C1, C2 input. So these are the inputs from process monitor.
No, these are not from process monitor.
This is locally, right? So
Yes.
we are not taking anything from the outside.
Nothing.
Nothing.
Nothing. No input from outside is required. In SRAM, the variations are up to such a large extent that you cannot rely on a different location sensor to operate such sensitive instruments like retention noise margin.
Okay. So my question was actually coming on from in a similar way what was the previous question, that if you want to implement in a compiler, like for different memory sizes,
Yes.
can we use something like process monitor to, bifurcate this tracking block uh, so that it works for different kind of macro sizes?
This particular tracking block, this particular tracking block
Yeah, for different
can
sizes.
be made, placed outside the SRM block, and these control signals, what I say, this one, this is placed outside the SRAM. This is the arrangement showing that this is used outside SRAM in SOC somewhere. This is generated, but very near to this memory. This should not be very far to the memory. Near to the memory, if there is a bunch of memory array is placed over here, memory blocks, then you need to place this one like your best caller stands, this one besides this, and these control signals, these will be like input pins to the memory.
No, no, Ashish, maybe I should rephrase the question. So suppose in this case you have 5 and 2 bit cells, and you have a stack of 4 diodes.
Yes.
Right. That is for specific macro size.
Yes, yes.
Like.
Yes.
So for compiler you can have different sizes.
Yes.
Okay. So
Yes.
can we make use of some inputs at the SOC level to make changes? Like, let's say here it's 5 and 2 bit cell, and some other size we might need 256 bit cells and 5 diodes.
Yes, yes, yes.
A compiler specific design for this. This is macro specific.
Yeah. Compiler specific optimization can definitely be done within memory instance also. Within memory instance also, you can change the programmation of the number of these memory cells and the number of these diodes. And from the outside also, if you know what potential is required, since this is adaptive, so you are not aware actually what potential is going to be required. That's why these tracking columns are required. That is the reason. So you cannot pre-program that, okay, under this condition for this instance, this particular voltage is to be given. This information has to come dynamically. The way this imprint has gone into the silicon, this has to come adaptively from there itself.
It's adapt. Okay, thank you.
Any other questions? Thank you very much, Ashish, for this
Thank you.
excellent presentation.
Thanks,
Thank you.
Dr.
Just a quick announcement, the exhibit booth's lucky draw will take place in Hall 3 at 6 p.m. So please plan to be there, and hopefully luck will shower its wisdom on all of you. Now on to our next presentation, activity-based frequency scaler for network on-chip idle power reduction, Krishnan Anantanarayan.
Thank you all, and thank you for your time. Good evening, everybody. So I am Krishnan. Sorry?
Excuse me.
Yeah, thank you. So I am Krishnan, and today I'll be discussing one of the ideas for reducing the idle power for network on chip, and hence the title, activity-based frequency scaler for network on chip idle power reduction. So along with me, my mentor, Santosh Kumar Singh, has equally contributed in this work. He couldn't be here today due to some personal work. So this is the agenda for the discussion. So I'll be starting with the problem statement, and we'll be discussing two existing solutions and what is the solution which we proposed and what we are implementing in silicon, and we'll also talk about results, conclusion, and we can move on to the Q&A. So today we live in a world where when it comes to mobile devices, right, we want higher performance, lower power, and lower area, right? Of course, as we go below the technology node from nanometers to angstrom, we are anyways achieving the target of lower area, and with improved architectures, we are achieving the target of higher performances, right? Now coming to power. So there are already different methods available in the industry which is used extensively, such as clock gating or power domain on, power domain off, and all. And all those methods are extensively used to reduce the entire system power, right? And when we talk about mobile devices as of today, right? If we see on a broad perspective, right? We have so many variety of applications we run on these mobile devices. Let's say, for example, we run a 4K video, or we do a live stream, or we do some gaming activity, right? And it all comes at the cost of some amount of power being dissipated at each and every instant. Now, there are methods to reduce the dynamic power, So here I am going to talk about one of the methods to reduce the idle power of the network on chip. Now why network on chip? So typically in an SoC if we see, right, for different applications what we want to achieve, we have different components like CPU, which is the default in most of the SoC. Then we started moving on to GPUs for doing some dedicated, let's say, a gaming activity or a video processing activity. And even further, we moved to something like VPU, which is called a vision processing unit, which is very much dedicated for live video decoding and all other activities, right? Now, along with all these components, right, we also have memories in our system on chip. So typically, if you open up a system on chip architecture, you will see three major components, right? One is all the compute elements, such as CPU, GPU, VPUs and all. The memories where we actually store the metadata or some kind of information. And how do we connect them all? How do we communicate across all of these components, right? That is where the NOC comes into picture. Now, if you see the NOC, right, the fronts of NOC, what I call the memories or the CPUs or GPUs, run at very high frequencies, right? Typically in the range of gigahertz, like let's say 1 gigahertz to 2 gigahertz roughly. Now, even the NOC also has to run at such a high frequency, otherwise it will not meet the throughput requirements of your system. So now we have established the fact that we need a NOC in a SoC and it has to run at very high frequencies. Now again, as I was saying, right, the performance of NOC plays a very important role because it essentially routes your data through the entire SoC, right? Now, so that's why it has to run at very high frequencies pertaining to, let's say, 1 gigahertz roughly. Now, the NOC consists of multiple clocks, and one of the clocks which we identified in our design was a system clock which was running at 1 gigahertz clock frequency, roughly on that range. Now what happens is, in some architectures we cannot clock gate this system clock. So it has to be kept running throughout the entire duration your system is on, which means you are going to lose a lot of power because whenever your system is in idle state, still you will be running this NOC system clock at roughly 1 gigahertz frequency and you will tend to lose a lot of idle power there. So hence we propose a solution where we do not clock gate the system clock of NOC, but we throttle down the frequencies based on the idle state of the NOC. And how do we achieve it? Let's see in the upcoming slides. So before that, I would like to discuss two industry-wide method which is used to do the NOC-based clock gating or reduce the idle power of NOC. One is the software-based clock gating, where whenever you see an inactivity in your NOC, the software typically monitors it and it will go and perform a clock gating and it will again ungate the clock based on some activity. Now, this is okay, but this kind of architecture or solution is not feasible where you cannot clock gate your system clock. Now, another method to achieve or reduce the idle power of NOC is by hardware multiplexing the crystal clock, which is typically, let's say, 24 megahertz or 18 megahertz, which is a very low frequency clock with your high frequency NOC system clock. Now, if you use this solution, this is good as long as you have a circuitry in your SoC which can control or take care of the inrush current or the sudden change in current which happens due to a sudden switching from a low frequency such as 18 megahertz to a high frequency such as 1 gigahertz. So if you do not have a circuitry which can take care of inrush current management, then this kind of solution is not feasible. So these are the two widely used methods in industry to reduce the NOC idle power. Now moving on to our solution, right? So when we identified this problem, what we did is, so in a NOC there is something called as an idle indicator which you can monitor. So based on your idle indicator value or the activity of your NOC, you can decide to throttle your knock system clock frequency to whatever software configured value you want. Now, how do we achieve it? You take the input as a idle indicator or the activity indicator. This is your frequency scalar model, which I'll talk about in the next slide. And the frequency scalar model will give out the values of the frequencies which the NOT system clock has to be running, and that goes to a clock module interface, which is typically glitch-free clock divider, and then the output of the clock module will go to the NOT system clock, which will take it to a lower frequency than whatever it was running at, right? Now, how does this frequency scalar module work? I'll also talk about this early wake indicator in a moment. So this is a very detailed description of what I've been talking about. So let's say you are in idle state where your knock is still doing some kind of activity, there is some transaction happening to the knock. Now let's say the knock goes to idle for a certain period of time, which means there is no transaction ongoing in the knock, right? So at that moment you can scale down your knock system clock frequency. But can you do it immediately? No, because there could be a short, let's say only one cycle delay in by the time the next transaction reaches to the knock, right? So to filter out any such noise, we also have something called a hysteresis counter, whose count value is programmable through software. And based on, let's say, once your idle indicator goes low, it will trigger your hysteresis counter, and once your hysteresis counter expires, you will start decrementing the frequency. Now, how do you decrement the frequency? How does it know to what value it has to go? Now, that can be controlled by the software. The software can come and tell, okay, from let's say 1 gigahertz, you have to go to let's say 500 megahertz or let's say 256 megahertz based on whatever your system conditions are or your system requirements are. Now, again, there is a provision made where you can control the step size in what, let's say you want to go to 500 megahertz, right, from 1000 megahertz. So you can either go directly in one step or you can go in multiple steps as well. So let's say you go from 1000 to 750 and then from 750 to 500. So that is also provisioned through software. Software can come and tell, okay, hey, you have to go to the prescribed frequency in let's say 5 steps or 1 step or 2 steps based on the system requirements. Again, there is one more provision what we have implemented where what is the interval between two consecutive increments or decrements, right? That also can be controlled. So that will give you a further fine tuning of your system requirements and the clock frequencies of the knock. Now again, so far we have seen the flow for how do we enter a low frequency state, right? Now how do we exit out of it? Now typically either the idle indicator has to go back high, and as soon as it goes back high, you will trigger the exit criteria and you will hit upon the exit condition. And once you hit the exit condition, again here, how do we want to throttle up the frequency? Whether you want to go in multiple steps, single steps, that is also again programmable. So the increment and decrement step sizes are completely independent, and those are again software programmable. Now again, typically what happens is you get the idle indicator of the knock toggles back to high only when a transaction reaches to knock. So now in this case, what happens is already your transaction has reached the knock and then you start waking up back. So you will have some performance issues there. So to mitigate that, we have come up with some idea called as early wake indicator, which can be triggered through as simple as something like a generic interrupt controller or let's say something like a PCIe or USB devices, which will come and say, hey, there is going to be a transaction which is coming to the knock, please wake up. So in that way, we can actually go back to the original frequency of the knock system clock even before an actual transaction reaches the knock. So in this way, we mitigate those kind of performance issues. Now, this is a simple waveform of what I have been explaining so far. So as I was saying, right, once the idle indicator goes low, we have a hysteresis counter, and based on the expiry condition of the hysteresis counter, we start incrementing the frequency. So, start decrementing the frequency. That is what the scenario 1 talks about. Now, scenario 2 talks about the exit scenario where you happen to exit through an idle indicator. So again, when idle indicator goes back to high, which means your transaction is actually reached in knock, and that can again lead to some performance issues, right? Now, again, this is again another example which I have put up just to show differentiation between the idle indicator and early wake indicator. So here, if you can see, the idle indicator is still low, but your early wake indicator has come, so you again throttle back to the required or prescribed frequency of the knock. Now, this is a very classic example where your idle indicator comes after a certain period of time, but your early wake indicator has already come. So this is still a very symbolic way of representation, not to any scale, but you can save these many clock cycles, in fact, actually, before your actual transaction reaches to knock. And in this way, by the time you achieve, you see a data transaction or a control transaction at the knock, your knock will already be up and running at 1 gigahertz or whatever frequencies it is. So these are the results, these are the waveforms which I wanted to show, and now talking about what we have implemented. So we implemented this particular design in TSMC 7 nanometer, and since this was part of a power management unit, we could time close it at 125 megahertz. And I'm pretty sure since the depth of the logic and the amount of combinational logic is pretty low here, it can be run at higher frequencies as well. Now, using this method, we could achieve, we could reduce the knock idle power by almost 24%, which is a very significant savings when it comes to SOC power as a key index of your system design, right? And as we had the features of early wake indicator as well, we could not see any we could not see any performance being impacted. We could not see any transactions being corrupted or lost or anything we could not observe. And again, with all the provisions of software where you can fine tune the step size and you can determine whether how the interval between two consecutive increment or decrement, the step size of increment or decrement, with all these features, right? We can fine tune the we actually fine tune the silicon to the optimal value, so that we did not see any performance impact, and at the same time we could save almost 24% of the idle power. And this kind of design is an plug and place IP kind of a design where in any place where due to some architectural limitations, if we cannot do a clock gating, then this IP can be used in as a replacement for it, and we could still achieve some power savings out of it. That's all I wanted to discuss. I'm open for Q&A. Thank you.
The frequency scaler model you were showing, right? Is that part of within the NOC or is it implemented outside the NOC?
So this is your NOC, right? Now this whole thing comes as a part of power management unit. You can skip the clock divider circuit over there. This frequency scaler model or whatever this FSM I showed you, right? This comes as a part of the power management unit. This is not part of the NOC.
So in this flow chart, when you are decrementing the frequency, when you go in steps, you need to start the hysteresis counter for each divider, right? Like that was not shown. Is that maybe intentional? Like you don't want to complicate the flow chart, or?
Right. So I didn't want to complicate the flowchart, but as you said, right? So let's say your step size is 2. So once you go from let's say 1000 to 750, you need to have some kind of counter-based mechanism which will keep track of okay, what is the next step size, and in what how many cycles later I need to go and decrement change the value of the clock frequency. So just not to complicate the flowchart and to keep it simple, and to keep it at a very algorithmic level, I did not put it in this particular diagram.
Okay, and while incrementing the frequency, will you go to the max possible frequency in one step, or you will go in steps again actually?
While incrementing or decrementing?
Incrementing the frequency.
So exactly. So while decrementing, even if you come back in one step, if you go down in one step, right? That we do not see any possible scenarios of a sudden current change because you are decrementing the frequency. But in this case, where you increment the frequency, right? So let's say you are at 100 megahertz now, at the lowest possible scale. You go to 1 gigahertz. There is a possibility where, because of this sudden or high frequency change, you might draw a substantial current in your voltage rail, which might impact, which might cause a di by dt issue, sudden changing current, which might hamper your system. So as this step size provision is especially meant and very valuable when you increment your frequency. So we cannot, so you can still go, but you have to ensure that there is no di by dt issue occurring. So let's say you are going from 900 to 1000 megahertz, right? In that scenario, it is okay to go in one step, but it might not be advisable when you want to go from, let's say, 100 megahertz to 1 gigahertz. So again, it depends on your system requirements and what state you are in before you increment back your frequency.
But if you go in steps, like maybe then you will be having this hysteresis counter to go step by step, then it will have an performance impact, right? Like because it will take a time to go to restore it to original frequency.
Correct, exactly. So that is why we have provisioned this early wake indicator, right? Which will kind of mitigate all these kind of issues over there. So if you are purely relying on the idle indicator, which will toggle or trigger only when an actual transaction reaches to knock, what you are saying is absolutely true. We will have an impact on the performance. But to mitigate that exact same issue, we have this concept called early wake indicator, which can be triggered to, let's say, a JIC, right? A generic interrupt controller, or some kind of a sideband signal coming from somewhere in the design, which can help solve this kind of performance issues.
But only in that case, early indicator should be early enough to restore its frequency to original. Otherwise, even with early indicator, you will have a performance impact actually.
Correct, that is correct. So, so here the idea is that we work very closely with the firmware or the software or the telemetry team, right? Who actually keeps track of all these early wake indicators, and we can always fine tune it, based on what system conditions are, what system requirements are, and yes, and still after that, there might be a scenario where, early wake indicator is coming, let's say, few cycles delayed, and that is unavoidable, and in that circumstance, we might end up losing, 1 or 2 cycles or whatever scalable size of the clock cycles before we go back to the maximum frequency, and by that time, the transaction might have actually reached the knock.
So, at what level this clock frequency scaling can be applied? Can it be applied at the final user level or the application level, or is it at the system designer level?
This is more from a system designer level. At user level, we would not want the user to control it through a software-based register. But again, having said that, we will have the some level of control like firmware, or let's say a system control unit, something like a system control unit where we have some kind of a microcontroller-based logic decision making, right? Those have the freedom to come and write the software values on how to increment or what step size or to what frequencies to go to. But typically at user level, at a user application level, we would not want to expose these level details to be given.
So in that case, what are the guidelines you give to the system designer to ensure that there is no inrush current, and what are the limits for the inrush current? So who determines those?
Right. So, if you ask me the exact limits for determining the ingress current values and what are the threshold, that has to come from the SOC requirements or system, whatever the SOC is targeted for, what are the voltage rails being used, what are the different workloads being used. But typically, we would not want it to, jump from, let's say, a crystal clock frequency to a, let's say, 5x of it or 4x of it. So again, these guidelines has to be fine-tuned very precisely for the system requirements. So in this particular scenarios where what we had observed, right, we could go from, let's say, 100 megahertz to 300 megahertz jump directly without causing a significant di by dt, right? And that was more from a simulation observations, GLS simulation observations and all what we had done. So again, I think to answer your question precisely, it's more about what system, what is your SOC voltage rails, what is the frequency all these components are running at. And I think we can empirically come up with some numbers and we can say, hey, you should not jump, let's say, from frequency A to frequency B directly for this kind of, with this kind of a design.
Yeah, so basically this is a very specific solution for a particular design.
Right, because it has to be that way, right?
Yeah,
because all different SOCs cater different workload requirements and different performance requirements, right?
Yeah, sure.
So that's why I said it's a plug and play IP, so it can be putting anywhere where you want to use this kind of designs.
So your architecture, like for this particular like application, is it like a single NOC or do you have multiple NOCs in the architecture?
Right. So in this architecture, what we have where we implemented this design was a single NOC design. But again, this can be extended to multi-NOC design very easily. It's all scalable.
Any other questions? Okay, thanks very much, Krishnan. Thank you very much. Our next presentation is optimal clock tree synthesis for high frequency SOCs. Nagateja Babu.
Warm welcome to everyone. So I am Lakshmi Sarvani. We are part of Intel team. So we are here to put forward our work on optimal clock tree synthesis, which is targeted for high frequency SOCs. Me and my colleagues will give you the particulars. So our object of interest is a system on chip which is used in mobile and server platforms and operates at 2 to 5 gigahertz frequencies, and it is targeted with low power budgets. In the SOCs, 30 to 50% of the performance is lost due to inefficiencies of the clock network. So, and in addition to that, there is a significant amount of power overhead on the total dynamic power budget and introduction of latencies. Power and performance are the key parameters in contemporary designs. So, improving the clock network quality can improve the PPA of the entire SOC, and clock network power takes a major portion of the clock power. So, in an SOC, clock is the most complex structure as it influences every part of the system from timing closure to peak power demand and chip architecture to layout. So designs of all sizes and with process technologies face these clock challenges, and today what is being done to address these challenges is over designing of the system is done, which creates additional overhead on power and area, and it also limits the maximum clock frequency and it restricts the performance. So here in SOCs, we observe on-chip clock on OCV variance and electromigration, clock jitter, clock skew, all increase with lower node technologies. So our strategy is to employ a robust clock network structure which can target all the end-to-end digital clock network issues and provide a better PPA. So here the main objective of CTS in PNR flow is to build a clock tree which has a minimum latency, minimum skew, and it should have maximum shared path with low power dissipation. So traditional clock tree which is built here is not optimal for designs which have higher clock frequencies and which have large number of sinks. And in designs where the sinks are spread across all over the clock area, macro area, traditional CTS is useful in the way as it is very simple to implement, and it gives us better clocking, better clock gating. But it is very prone to OCV challenges because of more divergence, and it has higher insertion delays, and it is very difficult to meet the skew targets. So in the mesh network, we have a network of pre-mesh drivers which drive the clock signal from the clock route to the mesh structure. So here you can observe these are the mesh drivers, and this is the network of pre-mesh drivers which take the clock route, clock signal from the clock route to the input of the mesh drivers. So the output of the mesh drivers are shorted together to form a metal mesh. So the mesh is a metal structure which distributes the clock signal all over our block using horizontal and metal stripes. So here multi-source clock tree synthesis is a hybrid approach which uses best of the both conventional clock tree and mesh structure. So here we have built the clock tree for primary clock source. So this is built in two stages. One is a global tree and the next one is a local tree. So the global tree, here it is built from the clock root pin to the tab drivers. So the tab drivers are highlighted in blue colors. These tab drivers in turn drive a large number of sinks. So the local tree is built from the tab drivers to the sink points. The sink points are highlighted in the pink color. So, and the intermediate green color highlighted are the H tree drivers. So the clock structure characteristics include this is an electrically symmetric clock tree which has enhanced insertion delays and skew values, and it has minimum OCV because from the path from the clock route to the tab driver is the common path, and due to the maximum common path we can reduce the OCV. So here we have done several fine tuning to obtain best QOR. The first one is H tree driver selection. This gives us a trade-off between the power and latency. So we have used 24x drivers in our clock path, and then NDR routing rules which give us routing resources versus latency trade-off, and then we have used only inverters in the clock path and mix of both. So we have observed that only inverters in the clock path has given us better QOR, and then we have optimized the max clock net length in order to reduce the effects of antenna and crosstalk. So the clock network which we have built is applicable to blocks of any shape and size. So the input for our method is placement dB or pre-CTS dB. So this is the flowchart for our process. So here we have 7 steps. So in the first step we give the clock tree specifications. So here the user has a provision to provide how many tab drivers he want to create and what is the strength, what is the capacity the one tab driver can drive in X direction and Y direction. That is taken in terms of sink box and sink box area. These are the two parameters which are given by user, and the second one is CTS configuration. So here we give the CTS balance points, CTS skew groups, and then we give the routing NDR routing rules followed by the transition values for the clock. And in the fifth step, set multi-source clock tap options. The tab driver allocation is done. So this is the main stage where our global tree is built, and in the next stage synthesize multi-source clock tabs. Here the local tree from the tab drivers to the local sinks is built within minimum levels, around 3 to 6 levels the tree is built here. And in the last stage, after the tree is built, data optimization is done. So during the construction of our clock network, we have considered the below parameters to obtain a better QOR for our blocks. Yeah. So here, as presented earlier, in the step 2 of the flow chart, there is a CTS configuration, and there we have mentioned the sync box and sync box area, where the user can give the coordinates in which we can build the tab drivers. So on the inputs given from the user, there are various configurations, and out of which we have obtained that 2 to 6 configuration is a better one when compared to 3 to 6 and 4 cross 6. And now my colleague Teja will give you the experimental results of the block.
Okay, this is the clocking architecture we have implemented, and in the next slide you can see the global HT construction from right from the clock port till the tab drivers. So the highlighted locations in the blue color are the tab drivers. From the tab drivers to the sinks, the clock distribution is through local tree, and in the next slide you can see that the highlighted sinks which are driven by their nearest tab driver. Majorly timing and power are the most important criteria which we taken into the consideration while we analyzing any clock tree. So with the optimal CTS we can able to achieve insertion delay reduction of 35% around, and also setup skew 47% and whole skew 64%. There is a reduction, and we can also able to reduce the power to 8% and the clock power to 5%. So with optimal CTS, the total negative slack has been came down to 5.27 ns in the setup scenario, and also from 292 ns to 110 ns in the whole scenario. So while number of violating paths also have been came down to 1480 paths in the setup scenario, and in the whole scenario it came down to 10k paths. So total buffers and inverters used to build the clock tree has also been reduced significantly, and the number of levels to build the clock tree has also been reduced to 19, and which in turn reduces the clock reporter count. We can also able to preserve the routing resources. So finally, our clock tree created a more structured clock distribution, and we can able to create a balanced clock tree for rectilinear floor plans also. So these are the percentages improvement in the routing resources and the power and the latency in the total negative slack. So which shows timing and power improvement in the both for this optimal CTS. So there is also a scope for improvement by automating the tab driver locations with design space optimization algorithm, and so which will reduce the manual efforts of the design engineers and also improves the runtime.
Any questions, please?
Which tool you use to implement this? Yeah, because in Cadence, right, there is a FlexX flow. Flex. So
Cadence has a flex tree solution. In Synopsys, you have a different solution. Okay, we have taken the best recipe. It's only your placement DB, whichever tool it is coming. It doesn't. We have written our own algorithm where it only chooses which tool. What is the tool input? Then automatically it will check the box, and then tap allocation happens. And the default, and there is a problem with the today's tool is whenever you do the tap allocation, from the tap to the sinks, it is not equally distributed. Which means, see, ideally the tap allocation should happen such a way that all sinks has to get distributed along all the taps, which doesn't happen as of today. Our flow or our algorithm, the way we have built up the algorithm in-house, is such a way that wherever there is not equal number of taps, the extra tap will get inserted, so that will compensate for that. And from the root to the tap, it's a common path, so you will have a better OCV.
Okay, thank you.
So how do you handle ECOs at a late stage, and then how much impact you will have on this clock tree? I mean, like, do you have to again start from the beginning, or can you actually do a kind of on whatever you have, can you do an incremental one?
So as of today, what we have done is the ECO cycle. See, that's the reason our skew targets is around about 70 to 80 PS is the skew target for N7 node, which we are targeting at. Okay, so we haven't seen a scenario where we haven't seen crossing even we are better the limits than the 70-80 PS limit, but we have not crossed beyond that. So when you go to ECFS, if you have to touch the clock network, yes, it's a difficult approach. But our today's target is that we are way beyond the the given targets basically.
Okay, but currently you have not gone through ECO cycle
We have
yet.
gone through the ECO cycle. We have gone through the ECO cycle. The thing is like the clock network, when you go to the ECO cycle, the clock network has to be touched.
Correct.
Right? Now, if you are meeting the limits, okay, then there is no point of going to the ECO cycle, right?
Okay.
Now, say for example, can you show us the buffer? We were using the traditional CTS, okay, where you don't have the control over the countdown. So this is the traditional CTS which we were, there was no control over the depth. So what we have to go always is we have to go back, reiterate, and then we used to prune everything. So the problem with the hold insertion, the hold buffer insertion was due to the skews not getting optimized. Today our skew, can you go to the previous slide? If you see our hold skew improvement, it's around about 64 to 65% improvement where you can see. That itself will give you the, you can see the scenario that the kind of improvement which we had using this hybrid CTS model.
Okay, and what was the DFT architecture that was used? Was it like so did it have any impact for the DFT?
No, we did not have.
Okay.
I think you better to compare with the FlexX because it's very simple. Obviously, we'll see this much difference.
One second. Can you go back? Can you go back? This is the Flex solution itself.
Okay.
This is the automated way which we have done. This is the Flex one from the CDN tool. Yeah. This is the hybrid CTS from the Synopsys tool. We have both the versions. It's not. It's not specific. It's not a tool specific. This hybrid CTS is specific to any tool. We have chosen the algorithm in such a way.
Yeah, I mean to compare the results just to the algorithm,
You want to
which is automatic, and your algorithm, how
Sure.
it will.
Sure.
You
Okay.
can see that.
Yes. Yes. See. Okay. Let me show you. So the one which is shown here is a kind of a squarish shape. The earlier slide was kind of a rectilinear. We have a tubular shapes, everything. Now the maximum level what it can go is 3 or 4 levels till the tap driver. From the tap driver to any sink, it will cover up to another 3 to 4 levels. Which means from the root to the sink, you are covering up to 8 levels, out of which 4 levels is going for CRPR, and then 4 or 5 levels you are reaching up to your sink, to the sink point. Okay. Yeah, we have checked that, but we could not capture the results over here. When you say optimal cut point till the structure, till the tap point you're mentioning. Okay. Can you go to the previous slide, please? See, if you see here, I mean, if you see, you have multiple cut points here, right? You have a different configurations there. You can see 2 cross 3, you can see 3 cross 6 configuration, you can see 4 cross 6 configuration over here. When I say 2 cross 6, 2 rows and 6 columns, 3 rows and 6 columns, and 4 rows and 6 columns. Now this depends on the block space and block size, what kind of block shape and size which you are using it. Okay, yeah.
Just a comment. Like, so one of the things that you mentioned is like it's tool agnostic, right? Like, but then on the other hand, it's a multi-objective optimization problem that you're trying to solve, right? So did you try to formulate the whole problem and see like how to solve it in a general sense? Yeah. So you said like there is a customized algorithm and things like this, right? So did you try to see it in because it's an optimization problem anyway, right? So did you see it in a general sense, like what kind of like optimization problem are you trying to solve?
Thanks very much for an excellent presentation, Lakshmi, Nagateja Babu and Subha. Thank you very much. So we'll move on to our next paper, Implementation of Multiple DFT Techniques for Power Efficient Testing, Moksh Sancheti. Is Moksh here?
Good evening, one and all present here. I am Moksh Sancheti from Info Chips, Gujarat, and I am here today to share some of the learnings and experience on my implementation of multiple DFT techniques for power efficient testing. The agenda will be like overview, problem statement, some of the low power techniques, and at last the results and the conclusion. So to start with, like the power consumption, like during the structural testing is generally higher than the functional testing. Structural testing means the DFT testing. And actually the power like dynamic and static. Static is due to the leakage, but we will focus over the dynamic, what is due to the toggling activity. Now from the design for test perspective, it's like mainly related to the like there are no correlation between the consecutive test vectors or like non-functional clocking during the test mode or the DFT circuit which has been used intensively, or the for time efficient testing we are concurrently testing multiple like blocks together in the design, and the compression which has been like multiple things due to which the dynamic power is increasing. So now what the issue is, like we see that power is a major thing, all of having our power in their topic of discussion. So like due to the elevation in the power, actually the die temperature will also increase, and due to which then can be chip damage or the reduced reliability or the performance degradation or the yield loss. So now specifically talking about the DFT, so the DFT inserted circuitry with the power is due to either the shifting or like the capture. So for the shift cycles, like there are multiple low power techniques which are being used. So the X filling, Q gating, low power scan compression, or the scan segmentation, scan clock splitting, and the staggered clocking. Now out of these techniques, the X filling, Q gating, and the low power scan compression can be configured for the low power shift, and if the EDA tools are providing support for that, so we will be mainly looking on that. So now for all of these techniques, the scan insertion step needs to be configured properly so that the needs to be properly chosen, because sometimes it's not necessary that using one of the techniques will fulfill the low power requirements. So you may need to use the multiple low power techniques combined together. So the scan insertion configurations needs to be chosen properly, because each technique will have its advantages as well as the disadvantage. And combination of this, all the techniques may affect the DFT results, such as the power metrics or the area overhead, test coverage, and the test patterns. So, a strategic approach will be needed. So the low power scan compression actually we are using to reduce the test access time and the TDV. So the compression can also be configured for the low power shifting. So so during the scan insertion, you need to specify the configuration for the low power. So in accordance to that, the hardware will be inserted, and the basic idea is like during the shifting, some of the chains will be loaded with the constant 0. So whenever the loading of that, a fixed value will be loaded, due to which there will be no toggling. So in each of the patterns, some of the scan chains will be restricted from the toggling activity. So only particular like this blue and like white, some of them only will be toggled, rest of them will be loaded with the constant 0. So in accordance to the parameters whatever you have given, the controller will be able to control the amount of the toggling activity and reduce the shift power. So to have the finer control over the larger number of scan chains, additional hardware which is implemented for the low power will be increasing. So and the ATPG power needs also to be configured in accordance to the scan insertion, otherwise there can be increase in the total test patterns, or there can be the reduced in the shift power. We will see how. So to starting with the comparison, so for the low power enabled, the average power of the shifting was like 13.49, and if we are disabling it is like 47.27. Now if we go, like for example, if I am giving the scan percentage parameter as 15 percentages, and in accordance to that, if I am keeping like 15% during ATPG, then the like percentages, the shift, the total amount of design which will be toggling is only 14.52. But if I don't give the ATPG parameters in accordance to the scan, then the power will be abruptly increasing. So the ATPG parameters needs also to be taken care. And along with that, if you see, that if you need the finer control over the shift power, then the amount of hardware which will be increasing, like for example 10%, then 125 of the total registers will be inserted, which is not the case for the 30%. So if you need more of the shift control, then the amount of hardware will be which is inserted, it will increase. And if the ATPG parameters, for example, if you see if they're not in accordance to the scan, then the simulated patterns and the discarded patterns are also increasing. Along with that, now it's not that you can straight away use this technique. There are certain disadvantages, as I mentioned. So if you see, during the shifting, there will be required more of the shifting cycles to shift from this architecture, the low power registers. So for that, like for example, if there are low power bits like 100, then the total of 82 cycles will be needing. So in that case, there is a provision that you can have a separate data, like the control data channel, through which only the low power bits will be shifted. So there are certain things which can also be taken care during the scan insertion. Like moving to the next technique is the X filling. Now the X filling, like for the test patterns, it generally contains both the X bits, like the care bits and the don't care, like either 1 or 0. So this X, like this X bits can be filled with the random bits, which will to reduce the, if we are filling with the random bits, then it can adversely affect the switching power. So we will be using some of the techniques to fill that X bits. So straight away going to an example. So these are the filled boxes are the care bits which are essentially required in the patterns. So these empty boxes can be filled with the random. So if you are just filling it with the random, so 0, 1, 0, so it will increase the toggling activity. But if you are having the 1, 1, 1, so there is no toggling during the shifting. So in that way, the shifting power can be reduced. And in this, you don't need to have any additional architecture. You just need to manipulate the patterns, and you just need to give no additional hardware is architecture inserted. Only the patterns are been manipulated. But now, as you are filling the random bits, so the probability of like detection of the random filling like faults, it will get reduced. So the pattern count may increase. So the one of the last techniques. So one is the queue gating. So like during the shifting, there is no need to toggle the combinational logic. So to restrict that, you may have inserted some of the combinational logic which is controlled by the DFT inserted signals like scan enable. So whenever the shifting is ongoing, from here a constant value will be loaded. So it will disable the entire combinational logic from the toggling. So here you are not manipulating the patterns as we saw in the X filling, but you are inserting the additional hardware. So in accordance to that, the DFT area overhead will be there. So all these three techniques are like supportive by the tool, and we will see how like the results, some of the results by like combining all these three techniques. So these are the parameters which have been used for the experiments. So if you see, like multiple experiments are been done, but whenever I am using the X filling technique, the power, the shift switching power can be reduced to a greater extent as compared to whenever you do used with the other techniques. The power can be reduced more as compared to the other techniques. So as for the power, if we check, the X filling can be more helpful as compared to the other techniques. But now there are other comparison, like for the example, the area overhead. So X filling won't be having like any area overhead because it's just a manipulation of the pattern, but the low power scan compression as well as the queue gating. So in that, there will be DFT area overhead because in the low power you are inserting some of the registers to control the low power, or for the queue gating you are inserting the additional combinational logic. So in that cases, there you will observe area overhead. And the last is the pattern count. So as mentioned in the X filling, the probability of detecting the random faults will be reduced. So the pattern count for the like the ATPG pattern counts will be increasing as compared to the other techniques. So like these three, the pattern count and the like the shift power matrix was like related to the area, was related to the DFT ATPG parameters, as well as the area overhead was the overall the scan inserted area overhead, which were used for the comparison of all of these techniques. So now, like as we saw, the multiple techniques can be combined together, but at the same time there will be a trade-off between the power matrix pattern count, test patterns, and the area overhead. So, but so how do you actually need to proceed further? For example, if I am given a design and there are certain specifications, so then which technique needs to be used, or how the combination of these techniques can be done? So if my requirement is such that I am only concerned about the power only, then X-filling is the right option, because it will be having the huge improvement in the shift power reduction. But if like the worries are about the pattern count, if the tester is not been supportive, or the testing time will be like more, then in that count X-filling cannot be used. And the other two techniques like Q gating, there will be no pattern count increase, but that will be the DFT area overhead increase. And yeah, the shift power reduction can be also improved with that. And the same case goes with the low power scan compression. So in that there will be definitely some more, because due to the compression also sometimes the pattern count will be increasing accordance to the design. But yes, there will be the DFT area overhead, and there can be, and there will be the improvement in the shift power reduction observed. So yeah, either the using one of these techniques, or combining of the combination of all of these techniques can be done for the low power shift majorly what we do. But you need to be careful, because each of them will have the advantages as well as the disadvantage what we observed. So like to conclude the presentation, I can say like that as the technology node has been scaling down, the number of transistors, the design complexity is increasing. So the power will be always as an important industrial aspect, because if the chip is manufactured properly, but if due to the testing the chip gets like the damage, or there are some yield issues, then the entire efforts along with the entire flow efforts and the time, everything will be like in vain. So testing needs to be done very much properly, by keeping mind in all of these things. So using all these existing techniques, by using the CAD support and some of the novel techniques, the testing power can be always reduced to a greater extent. But the thing will be, you just need to be careful by choosing the parameters, and you need to be strategic. So I'm open for the Q&A.
Most of the capabilities that you talked about, these are available in built-in in EDA tools, right? So this is more of user trying to find out different options to ensure that there is low power during the actual testing.
Yeah, correct. So like, yeah, the EDA tools are these three techniques. The EDA tool is always already been supportive, but sometimes we need to be careful while choosing these techniques, because at the end, if you when like the patterns have been submitted and all, after that, if you find that there are issues, so like before that and well in advance, in accordance to the design requirements, you can strategically approach towards how the low power shift can be like achieved.
So basically, I mean, how do you in the lab or as a DFT engineer understand that the excess power consumption is causing issues at the test time?
Okay, so like there will be always a constraint from pre-specified. For example, we can have a total of 15% of the minimum switching which has been allowed, and the above some of the percentages like 30 or some, that patterns cannot be worked, which will be always specified by for the design.
I mean, how do you develop that heuristic? I mean, why 15%? Why not 20%? How do you decide? Because anytime you're doing any of these interventions, you're losing test time, right? So how do you decide this is my optimal cut point where my test time is balanced against power requirement, and if I go further, I will indeed see problems?
So if you are using any of these techniques, then definitely there will be a trade-off between the other parameters. So for example, if by using any of one of the techniques, the testing time is increased as you say, but the power requirements can be met. So at that particular time, we can have the combination of one of two techniques, like in which the testing time can be reduced, and power power metrics can also be balanced with that.
Which can be dealt with even when the silicon is on the tester.
Yeah.
Q gating is something that you'll have to do before the tape out.
And same goes with the low power like compression, scan compression also, because for that also the additional hardware needs to be inserted.
So, what is the guideline in selecting what kind of Q gating you want? How many you can afford to add, and what will be the advantage of them on the final silicon, because you don't have the silicon right now, right? And then what are the parameters which is actually taken into consideration when you define that?
Okay. So like talking about the Q gating, for example, then each of the flop, if is a sequential element, will have a fan out. So we can have like a threshold, like if any particular sequential flop is having a fan out, for example, beyond say 500 or 1000. So we can select that particular flops for the Q gate insertion. Because Q gate we will be adding the additional combinational logic, which will increase the DFT area overhead. So we can have a particular threshold, like for example, beyond this particular fan out, if the like a flop is having, or the sequential element is having a fan out beyond this particular thing, then only the Q gate insertion can be done, needs to be done.
So the gate which gets added will also add to the leakage of the overall chip, right? Because it's a gate which will always be there even in the functional mode, and it will keep getting the data. So basically you are adding to the leakage problem as well.
Yeah. So that's why, like, not for example, if you are having like 150 flops in the design, then we cannot like straight away add to all of the, to control the low power, for having a low power shift, like adding the gates to all of them. We need to be like strategic. If we are concerned only with the low power shifting only, then we will like select, for example, 10 of them or 15 of them for the Q gate insertion. Otherwise, as you mentioned, that by adding like like adding for all of them, the leakage power will be increased.
Pushing constant data into the chains, which compressor technology have you considered? Because the compressor or decompressor logic, the way they get implemented, usually doesn't get the data from the same cell always. And if you want to push in a constant data into an internal chain, then probably you might take away some flexibility from the decompressor logic itself. The flexibility of giving you an optimal pattern is getting taken away by forcing the tool to push the constant data into certain cells.
Yeah, like correct. So for example, in the decompressor, as you mentioned, that there will be the AND gates inserted to to load the constant values. So if you are using the like for example low power scan compression, so as compared to compression, there we may see the increase in the pattern count. Because earlier with the limited number of pattern counts you will like achieve the coverage, but now as you are limiting, so like switching off some of the scan chains, then the pattern count will be increased, because some more patterns will be required to like achieve that particular coverage. So like, but for like from the decompressor side, if you are concerned, then additional OR gates we can, additional AND gates are added to be like in layman language, which will limit, like which will load the constant values in the scan chains.
Thank you.
Thank you
Thanks a
so
lot.
much.
Thank you for
Thank
the
you so
lovely
much.
presentation. Okay, we are down to the last presentation for today. It's Advanced ATPG Fault Models, Kishan, Krishnakant, and Soumya.
So hello everyone. So first of all, I would like to thank you all for attending this presentation. So my name is Krishnakant Kori and I'm from the InfoChips. And today I will be presenting the topic Advanced ATPG Fault Models. So with my colleague Kishan Mayani and Soumya Shah, we are presenting the Advanced ATPG Fault Models. Currently they are not present at the moment. So the agenda for today, we will go through why advanced fault model, then delay testing, small delay testing, then we will go with the cell level testing, and we will wrap it up with the conclusion. So first is why advanced fault model. So testing the chip with the ordinary fault models such as high coverage stuck-at fault models and transition fault model really help to identify the defective chips and deliver the error-free chips to the market. But with the current advancement in the technology, relying only on the ordinary fault models is not enough. So, and the key reasons are, first is application criticality. So once the chips are shipped to the market, these chips are integrated on a system level applications, and any flow into this chip has potential to be disastrous and can affect directly human lives. Then density headache. So as per the Moore's law, transistor counts are rises, and with the current advancement in the technology, new defects are introduced in our designs, which is not generally covered by our ordinary fault models. Higher frequency. So majority of chips nowadays are working on extremely high frequencies, and with this technology and high frequency, we have large number of critical paths on our design. And with the normal transition fault model, we are not able to cover all the delayed fault models. Then next is delay testing. So testing the chip with only testing the chip by identifying only the hard defects with the stuck-at fault model is not advisable, as timing failures can occur when our chip is working fine with this lower frequency, but it is failing timing when it is operates on higher frequencies. So we have transition delay fault models to identify this delay testing. So in the transition delay testing, we are targeting the defects on a specific node, which targets by identifying the time interval taken for transition from 0 to 1 or 1 to 0, and it is targeting only the gross delay due to the defect. Then another, we have path relay testing, and path relay testing verifies our cumulative propagation delay, total propagation delay along a path within the specified limit, and it is targeting the critical paths provided from the PD team. You can see in this below image, if we have any small delay on any specific node E, C, E or G, it will not affect the timing, but the small delay on C, E and G will affect the timing, as it will sum up and it will result in a large delay along a path. For path delay, we require critical path information from the PD team, and we will check whether these paths are correct or not, and if it is correct, we can directly load into the tool and perform the ATPG, path relay ATPG, and if there is any mismatch in the path, we can modify this path. We have to cover the delay testing, we already checked the transition delay and path delay. Then why we require the small delay defect testing, which is one of the advanced fault model. And to answer this question, let's look at the limitation of ordinary fault models. So the transition fault model detects slow to rise and slow to fall on the specific node, and it uses only the shortest path, which is not enough to make sure that it will affect the timing or not. And path delay, it detects the slow to rise and slow to fall on specific critical paths, but and we are reading the path delay reports to consider the path, but there are large number of possible paths in our design, so it is not possible to specify and read all the critical paths. And small delays are nothing but it is a minor substitution in the delay, standard cell delay, due to the on-chip variations, and it is targeting the timings with the minimum slack. It is targeting the faults on a path with the minimum timing slack, and it is also called as a timing aware ATPG because we are reading the slack based information into our ATPG tool. So this graph is showing the distribution of faults based on the slack information. So you can see there are still more number of faults which falls inside the with the lesser slack. And to understand the small delay defect methodology, let's look at this figure. To specifically target the fault at the any specific location, in this image it is marked with the red cross. So we have total 3 different paths to target the faults on a red cross mark. And you can see based on the clock diagram, there are 3 possible paths, and we have minimum slack path on we have maximum timing delay on path 1 so we have minimum slack value, and path 3 has maximum timing slack. So our ordinary fault models like transition fault model, it will only it will choose the shortest and easiest path to sensitize this fault site marked with the red cross, and any physical defect on path 1 which causing the small delay will be missed out because we are only targeting the shortest path. It is necessary to and our small delay defect testing methodology will perform the ATPG and target this fault on a maximum timing slack path, which is path 1. So you can see in a clock diagram, we have minimum slack. For each faults, we have minimum slack values, and we are providing the timing margin information. So tool will control the which faults we want to target to perform the small delay defect. And we can also specify any maximum delta value to give the additional relaxation to the tool. So if our fault is not detected from the path 1, tool will relax its detection path and it will target from the path 2. But it is still better than the path 3 to identify the small delays in our design. Then we have cell level testing. So cell level testing is used to generate deterministic defective deterministic pattern based on the defect oriented faults on the defect oriented faults on the cell internal for the cell internal defects, and based on the physical layout information to extract the transistor level netlist. And the goal of the cell level test is simple: to identify to improve the quality of chips and to lower the DPPM, which is defective parts per million, and to improve the physical failure analysis capability. So before we go through the cell level testing, we have library generation flow for cell level. So it starts with the cell by reading the layout information for each standard cells. So cell layout information is available in a GDS2 format, and we will perform the layout extraction to get the transistor level parasitic netlist, and after extraction of this parasitic netlist, we will analyze which defect need to be injected during the ATPG and need to perform the simulation. Now next is analog fault simulation. So analog fault simulation will perform the exhaustive simulation to identify the all possible input combination to detect all the possible cell internal defects. Now based on one of the study, it has been identified to that normal Stuckett fault model only requires the 4 possible inputs to check all the Stuckett 0 and Stuckett 1 faults on each nodes. But based on one of the study and experimental patterns, it is identified one of the cell internal bridge defect identified with the additional 000 pattern, which is not targeted by normal Stuckett patterns. Then another thing is there are 6 possible cell internal defects, which is open, bridge, transition drive, transistor leak, then port open and port bridge. So this is the after the cell library generation, UDFM generation, we will perform this cell over ATPG. So it will require flat model, which is netlist information. Then we will read the fault site information by reading the UDFM file generated by the library generation flow, and we will add all the faults and generate the patterns. And as I said, there is generating only the pattern, identifying the defective chip is not enough. We also need to identify what is the root cause. So there is a diagnosis flow, cell level diagnosis flow. So in the cell level diagnosis flow, we require flat model information. Then we will perform the simulation to identify that patterns are correct or not. And we will need to have the layout information, and to layout information we require cell level to generate the layout database. We again need to read the flat model information, and to create the layout database information we will require def file and lef file. LEF file consists of layout information, and def file consists of physical constraints in coordinates information. Then we will read this LDB file in our layout in our ATPG tool, and then we will set diagnosis options to perform the cell aware diagnosis, which will require UDFM file, and we will perform the cell aware diagnosis. So you can see and this below image, our normal diagnosis only reports the cell input and output pins information. But with the cell level diagnosis, it will also provide the metal and via informations, metal layer information, via information, coordinates information. So there are few benefits and impacts of cell level testing. So it targets the faults within the cell, which is not covered by normal structure and transition. It is superset of structure and transition, as it is also covering the faults of on the cell nodes. It will provide the better TPPM to improve the quality of chips and better diagnosis resolutions. And there are some impacts, like there are some additional timing and effort to generate the cell level library, and we have higher ATPG runtime, and it will increase test pattern count and test time, which is loaded on the ATE. So conclusion, identifying all the possible defect is a top priority for all the companies, and by adopting the advanced ATPG fault model, we can cover more number of defects and get the better coverage to improve the quality of chips. Now here is one of the result by targeting the small delay defect. So we have generated the majority of pattern with the small delay defect, and around 84% of coverage we have targeted by SDD, and additional top of pattern to achieve the 0.76 and total of 85% coverage. So majority of patterns we generated with the SDD fault model, and there is a delay effectiveness terminology, which is to identify. So here it is 31%. So 31% of fault in our design has been detected with this smallest slack path. So and there is a maximum timing margin value. So it has small delay defect has targeted the faults which is falling on the path with the minimum timing slack of 0.1 ns. As you can see with the cell aware and normal cell aware, this diagram shows the cell aware and normal fault count, and you can see in the blue image it is cell aware static faults, and in the red it is normal stucket faults. So you can see around there are too many faults which is covered by which is covered by cell aware static, and another is normal cell aware dynamic, which is similar to the transition, and we are covering around 653 million fault count, but in green it is normal transition, which is only covering the 74 million faults. So this is the runtime. So normal in the red it is showing the runtime for the normal stucket to generate the pattern on the normal stucket fault model, and the blue is cell aware static pattern generation time for cell aware static, and this is the coverage information. So with the additional 1.5 times in the blue we have cell level static information, which is around 1.5 times pattern count increase in the cell level, and in the normal stucket, and there is no much coverage drop, we can say here. So with this we can cover more number of defect and improve the test quality of the chip. And these are the references, and that's it from my side.
If you are using cell level based testing, we are targeting more number of faults. Will it account for more number of patterns? Then
Correct.
how you will, I mean, how will you account for that increasing in number of patterns? Whether targeting through cell level testing is and detecting these faults is very important, or we have to reduce the number of patterns based on the AT requirement. What would be the trade-off between these two?
Yeah, so the quality of chip will be the more matter for all the companies. And during the initial wafer sorting, we can we can separately check stucket and stucket as well as cell level static fault model. We can cover both. We can deliver both the patterns, stucket and cell level static patterns. But during the production, we can we can use the hybrid model. We can generate initially normal stucket fault pattern generation, and onto the top of that, we will fault simulate this stucket faults, stucket pattern onto the cell over session. So it will cell over normal stucket pattern has already covered some of the cell over defects, but we will perform the fault simulation, and then we will perform the top of pattern generation with the normal stucket. So it will reduce the pattern count, but with the additional identification of the defect.
Okay.
So we will use a hybrid model.
Okay, particularly in what applications we have to use you have told different fault models. So what based on application you'll be using different fault models. So when we have to switch on to this cell level based testing, because is it for some safety critical applications? Only in that case if we have to use for this cell level based testing, or whether it is fine to use transition or path delay fault based testing, it is enough to use those fault models.
So it also depends on the which technology node you are working. So if you are working on the lower technology nodes, there are more number of chances new defects are introduced in the chip. So in my previous 7 nanometer technology chip I worked, and I have targeted this small stucket fault model, transition fault model, path relay, but still I get the written part from the system level testing. So so it depends on the technology node. So currently all the companies are targeting for the cell level to ship the defective free chip to the market.
Okay, basically so hybrid mode of using the patterns will help in reducing the fault, I mean for fault detection and reducing the pattern coverage, and everything has to be taken care. So we have to opt for hybrid mode, right?
Yes, hybrid model will be good. Yeah.
Okay, thank you.
Any other questions? Okay, thank you very much. Thank you.
Thank you all.
Thank you for attending, and thanks to all the presenters. Now we'll have the memento presentation. So, and Santosh and Alex, thanks a lot for staying through the presentations and getting. So I'd request you to come and give the mementos to the presenters. So, thank you. The first one is Hemlata Murugan and team. Can you please come to the dais?
Nagteja Babu, Subba Ramkumar, and Lakshmi Sarvani. I think Subba already left. Shubhayu Das, Nandita Rao, and Sharad Sinha.
Noor Muhammad, Srihari, Ayesha, and Namrata. Kishan Mayani, Krishnakant Kori, and Soumya. This duty exercise, and after the judges look at the scores, the best paper award will be announced tomorrow. And have a good rest of the conference, and thank you for attending. Thank you.